Quantum superposition is a fundamental concept in quantum mechanics that describes how a particle can exist in multiple states simultaneously until a measurement is made. To understand this idea, imagine holding a coin. In everyday situations, when you flip the coin, it lands either on heads or tails. The coin, once it is settled, shows a clear single outcome. In contrast, in the quantum world, a particle, such as an electron, can exist in a state where it is effectively both heads and tails at the same time. In other words, until an observation is made, the particle does not have one definite state, it is in a combination of all possible states. A useful analogy is to consider a beam of light passing through a prism. Before the light is observed on a screen, it can spread out into a range of colors, with each color representing a different possible outcome. In the quantum realm, instead of a fixed color, a particle exists in a blend of all its possible states simultaneously. When a measurement is performed, this blend collapses into one specific outcome, much like the beam of light eventually settling on one dominant color when filtered by a specific instrument. The concept can also be compared to a stream of water that encounters a fork in its path. Imagine the stream splitting into several smaller streams, each following a different route. As long as the water flows freely, all these paths are active simultaneously. Only when the water is forced to follow one of the paths, perhaps by placing a barrier in all but one channel, does it become evident which route the water takes. In quantum mechanics, before measurement, the particle's path is not determined. It explores all possible routes at once. This idea is not just theoretical. Experiments with electrons and photons have repeatedly confirmed that particles do not have a single well-defined state until they interact with a measuring device. In the classic double-slit experiment, for example, a beam of particles such as electrons is directed at a barrier with two narrow slits. If no attempt is made to observe which slit an electron goes through, the electrons hitting the screen behind the barrier form an interference pattern, a series of alternating bright and dark bands that is characteristic of wave behavior. This interference pattern indicates that each electron has passed through both slits simultaneously, interfering with itself, and that its behavior was governed by a superposition of the two possible paths. When detectors are placed at the slits to determine the path of each electron, the interference pattern disappears. Instead, the electrons appear to behave like classical particles, passing through one slit or the other. This shift in behavior shows that the act of measurement forces the electron to adopt one definite state, effectively choosing one path over the other. The superposition of states is therefore not observable directly. It is revealed only by the potential for different outcomes before a measurement is made. Mathematically, quantum superposition is described using a wave function, a complex function that contains information about all possible states of the particle. The wave function allows scientists to calculate the probability of finding the particle in any given state when a measurement is taken. The probability is determined by taking the square of the absolute value of the wave function at a specific point. This method of calculating probabilities, known as the Bohm rule, has been confirmed by numerous experiments and forms a central part of the standard interpretation of quantum mechanics. In practical terms, the idea of superposition underpins much of modern technology. For instance, quantum computing relies on the principle that quantum bits, or qubits, can exist in a superposition of states. Unlike classical bits, which can be either 0 or 1, a qubit can represent both 0 and 1 simultaneously. This property allows quantum computers to process a vast number of possibilities at the same time, greatly enhancing their potential to solve complex problems that are beyond the reach of conventional computers. Another example is found in quantum cryptography. The security of quantum key distribution protocols relies on the fact that measuring a quantum system in a superposed state disturbs it. This disturbance can be detected, ensuring that any attempt at eavesdropping on the communication would be noticed. Thus, the principles of superposition not only deepen our understanding of the microscopic world, but also lead to practical applications that benefit modern technology. It is important to note that quantum superposition does not imply that a particle is in two distinct states in the classical sense. Instead, the particle exists in a state that is a linear combination or sum of all possible states. This combined state is maintained until an interaction such as a measurement causes the system to transition to a single state. The transition is not gradual, rather it is an abrupt change that occurs when a measurement is performed. The behavior described by quantum superposition challenges the way we normally think about objects. In our everyday experience, objects have clearly defined positions and states. However, at the quantum level, particles can be in multiple states at once, and the state observed depends on the type of measurement conducted. For example, an electron may be in a superposition of different positions, spins, or energies. Only when a specific property is measured does the electron settle into one of the possible states, and the other possibilities are not observed. This idea was one of the major departures from classical physics when quantum mechanics was developed in the early 20th century. Early quantum theorists had to come to terms with a reality where determinism was replaced by probabilities, and where particles could not be said to have definite properties until they were observed. This shift required a new way of thinking about the physical world, one that is best described by mathematics rather than everyday intuition. Experimental evidence for superposition is abundant. Techniques such as electron diffraction and interference experiments provide clear evidence that particles behave as if they are spread out over space in a wave-like manner. In these experiments, when particles such as electrons pass through a series of slits or interact with a crystalline structure, the resulting patterns on a detector can only be explained if the particles were in a superposed state before they were observed. In summary, quantum superposition is a key principle in quantum mechanics that describes how a particle can exist in multiple states at the same time until it is measured. Another captivating concept is wave-particle duality, which explains how light and matter can exhibit characteristics of both waves and particles. In everyday experience, objects appear as distinct, solid items with clear boundaries. However, when we explore the microscopic realm, we find that this distinction no longer applies. Instead, entities such as photons, particles of light, and electrons show properties that are sometimes wave-like and sometimes particle-like, depending on how they are measured. To understand this idea, consider the behavior of water in two different scenarios. When you disturb the surface of a calm pond, ripples spread out smoothly in concentric circles. These ripples are waves. They travel outward, interfere with each other, and display patterns like crests and troughs. In contrast, imagine throwing a small stone into the pond. The stone itself is a discrete object, and its impact is localized. In the microscopic world, light and electrons behave in a way that seems to combine both these aspects. One of the earliest pieces of evidence for wave-particle duality came from experiments with light. In the 19th century, scientists observed that light produces interference patterns when it passes through two closely spaced slits. When a coherent beam of light, such as that from a laser, is directed toward a barrier with two narrow openings, the light spreads out and overlaps on the other side. The overlapping waves interfere with one another, creating a pattern of alternating bright and dark fringes on a screen placed behind the barrier. This interference pattern is a classic signature of wave behavior. It is similar to the pattern formed when water waves overlap after passing through two gaps. Later, experiments revealed that light also behaves as if it were made of particles. In the photoelectric effect, when light shines on a metal surface, it ejects electrons from the material. The observations from these experiments could only be explained if light were made of individual packets of energy, called photons. Each photon carries a fixed amount of energy that is directly related to its frequency. In this way, light demonstrates a particle-like nature, where energy is transferred in discrete amounts rather than continuously. The dual behavior of light led to a puzzle: how can light behave both as a wave and as a particle? The solution to this puzzle is provided by the framework of quantum mechanics. In quantum theory, The description of light is given by a mathematical function known as the wave function. This function contains all the information about the light's possible behaviors. When no measurement is made, the wave function describes light as having the potential to exhibit a full range of outcomes. It is not limited to a single well-defined state. Depending on the experimental setup, the behavior of light can reveal its wave-like interference or its particle-like discrete energy packets. This duality is not exclusive to light. Electrons, which we often think of as tiny, point-like particles, also display wave-like properties. When electrons are fired at a barrier with two slits, they too form an interference pattern on a screen behind the barrier. This indicates that, much like light, electrons can exist in a state where they have the potential to travel through both slits simultaneously. When the electrons are not observed, their wave function spreads out and passes through both openings, creating an interference pattern. However, if detectors are placed at the slits to determine which one the electron passes through, the interference pattern disappears, and the electrons appear to behave like ordinary particles. To illustrate this further, consider a beam of light as it travels through a system of lenses and apertures. When the light is not being directly observed, it can be described by a spread-out wave that covers a range of possible paths. The light's wave function interferes with itself, resulting in regions where the intensity of light is high constructive interference and regions where it is low or absent destructive interference. This is similar to how a water wave can split into multiple waves when encountering an obstacle and then recombine to form complex patterns. When a measurement is performed, say by placing a detector in the path of the light, the act of measuring forces the light to choose a specific outcome. The wave function, which had previously encompassed many possibilities, appears to collapse, and the light is then detected as a particle at a specific location. This phenomenon is not a gradual transition, rather it is an abrupt change that occurs at the moment of measurement. The duality lies in the fact that the same quantum object can display either wave-like or particle-like properties, depending on how it is observed. The double-slit experiment serves as a prime example of this behavior. In one version of the experiment, light passes through two parallel slits and produces an interference pattern on a screen. In another version, if detectors are placed at the slits to record through which slit each photon passes, the interference pattern is replaced by two distinct clusters of impacts on the screen, one behind each slit. The presence or absence of the interference pattern depends entirely on whether the path of the particles is measured. This experiment clearly shows that the behavior of quantum objects is influenced by the experimental setup and the type of measurement performed. The explanation provided by wave-particle duality is central to many modern technologies. For example, in quantum computing, information is stored in quantum bits, or qubits, which can exist in a superposition of states. This means that a qubit can represent both 0 and 1 simultaneously, allowing quantum computers to perform many calculations at once. The wave-particle duality of electrons and photons is also harnessed in devices such as electron microscopes and lasers, where understanding the dual nature of these particles leads to improved performance in new applications. It is important to note that wave-particle duality does not imply that particles sometimes behave like waves and sometimes like particles in an arbitrary manner. Instead, the observed behavior is determined by the nature of the measurement itself. In situations designed to reveal wave characteristics, the wave nature becomes apparent. In experiments aimed at detecting particle properties, the particle nature is observed. The dual aspects are two sides of the same coin, fully described by the mathematical formalism of quantum mechanics. One way to think about this is to imagine a system that can be represented by a mathematical probability distribution. This distribution encodes all the possible outcomes of a measurement. In the case of light, the probability distribution can explain the formation of an interference pattern, while in the case of the photoelectric effect, it explains the release of electrons in discrete packets. The underlying mathematics does not force a strict division between waves and particles, rather it provides a unified description that accounts for both types of behavior. The concept of wave-particle duality fundamentally reshapes our understanding of the microscopic world. It challenges the classical view that objects must belong to one distinct category. Instead, quantum mechanics shows that the basic constituents of nature are not limited to being strictly waves or particles. They are quantum objects that embody a richer, more nuanced set of properties. This dual nature is an essential feature of the quantum realm, verified by numerous experiments and forming the basis for our modern understanding of physics. The next fundamental concept is Heisenberg's uncertainty principle, which explains why there is a limit to how precisely certain pairs of physical properties, like a particle's position and its momentum, can be known at the same time. In everyday life, we expect to measure things with great accuracy. However, in the microscopic world, when scientists try to pin down exactly where a tiny particle is and how fast it is moving, nature itself prevents both from being determined with absolute precision. Imagine trying to capture a clear photograph of a fast-moving object. If you use a very quick shutter speed, you can freeze the object and see exactly where it is, but you might not get enough information about how it's moving. Conversely, if you use a slower shutter speed, you capture its motion, but its exact position becomes blurred. In the quantum world, this kind of trade-off is not a flaw in our instruments, but a fundamental characteristic of particles themselves. One way to understand this is by picturing a beam of light. When light is not directly measured, it behaves like a spread-out wave that covers a range of positions. If you try to determine exactly where a particle of light is, the light's wave-like nature means it spreads out over a broader area in terms of its momentum. Its movement becomes less defined. Similarly, if you measure the momentum very precisely, the exact location of the particle becomes harder to pinpoint. This behavior is a natural consequence of the way particles are described in quantum mechanics. Instead of having a single fixed state, particles exist in a kind of built-in fuzziness. This means that nature simply does not allow us to know both the exact position and the exact momentum at the same time, no matter how advanced our measuring tools are. In practical terms, this principle has been confirmed in countless experiments. When scientists study electrons in atoms, for example, they always find that there is a limit to how precisely both the position and the momentum can be measured simultaneously. This intrinsic uncertainty is not due to experimental mistakes or limitations in technology. It is a fundamental property of the quantum world. The uncertainty principle also has significant implications for technology. In devices like electron microscopes, the fact that there is a limit to the precision of an electron's position or momentum places a natural limit on the resolution of the images produced. Engineers design these instruments by taking the inherent uncertainty into account, striving to balance the need for precision with the unavoidable blur imposed by quantum mechanics. Another striking example is found in quantum cryptography. In certain secure communication protocols, the fact that measuring a quantum system disturbs it is used as a safeguard. When someone tries to intercept the information encoded in a quantum state, the act of measuring will disturb that state in a detectable way, alerting the communicating parties to the interference. This practical use of the uncertainty principle underlines its importance in modern technology. It is important to understand that this principle is not a temporary limitation that might be overcome with better tools or techniques. Instead, it reflects a basic aspect of how nature operates at very small scales. The uncertainty is not due to the imperfections of our devices, but is built into the very fabric of the quantum world. The principle also extends beyond just position and momentum. Similar limitations exist for other pairs of properties, such as the energy of a particle and the time over which it is measured. This means that even when studying processes like radioactive decay or the behavior of unstable particles, there is a natural limit to the precision with which certain characteristics can be known. Heisenberg's uncertainty principle fundamentally changes our approach to the microscopic world. In classical physics, objects are expected to have well-defined properties at all times. In contrast, quantum mechanics reveals a world where certainty is replaced by a spectrum of possibilities and where some properties remain inherently uncertain until measured. This shift in perspective is one of the key reasons why the quantum world is so distinct from our everyday experience. The consequences of this principle are not just theoretical, they have practical effects in many areas of science and technology. For example, in experiments that measure the properties of subatomic particles, the uncertainty principle sets a clear limit on what can be known. Scientists have learned to design experiments that work within these limits, using statistical methods to extract meaningful information from the inherent uncertainty. The next intriguing concept is the Schrödinger's cat paradox, a thought experiment that illustrates the strange and non-intuitive nature of quantum mechanics. It was designed to highlight how the rules governing very small particles can lead to unusual predictions when applied to everyday objects. The experiment imagines a scenario where a cat is placed in a sealed box, along with a mechanism that has a random quantum event at its heart. In the setup, a tiny amount of a radioactive substance is included in the box. This substance has a fixed probability of decaying over a given period. If an atom in the substance decays, it triggers a mechanism that breaks a small vial of poison, which would then kill the cat. If no decay occurs, the cat remains unharmed. According to quantum mechanics, before we open the box, the system is described by a wave function that includes both possibilities. The decay has occurred and the decay has not occurred. As a result, the state of the system is a combination or superposition of two outcomes, one in which the cat is alive and one in which the cat is dead. The key point of this paradox is that in the quantum realm, particles do not have definite properties until a measurement is made. Here, the radioactive decay is a quantum event. When left unobserved, it is not simply in one state or the other, it exists in a mixture of both. Extending this idea to the entire setup, including the cat, means that the cat is described as being in a superposition of alive and dead states simultaneously. This thought experiment challenges our everyday understanding because, in the macroscopic world, we expect objects to have definite states. We know that a cat is either alive or dead, not both at the same time. Schrödinger's point was to show that applying the rules of quantum mechanics to everyday objects leads to a result that seems absurd. It is important to understand that the paradox is not intended as a practical experiment, but rather as a way to illustrate the unusual consequences of quantum theory. One way to think about the paradox is to focus on the role of observation in quantum mechanics. In the quantum framework, the act of measuring or observing a system forces it to adopt a specific state. In the case of Schrödinger cat, when the box is opened, the observer finds the cat either alive or dead. Prior to opening the box, however, the system is not in one definite state. Instead, it is described by a combined state that reflects both possibilities. This is a direct consequence of how quantum systems are described mathematically and conceptually. Another perspective is to consider that the entire system, including the radioactive substance, the mechanism, and the cat, is treated as one quantum system. In quantum mechanics, a system is only said to have a definite property once an interaction such as a measurement occurs. Until that point, the system remains in a superposition of all the possible outcomes. When an observer finally interacts with the system by opening the box, the wave function that describes the system collapses and the cat is found in one definite state. It is useful to compare this scenario to experiments that are performed with particles, such as electrons or photons. In these experiments, particles are often found to be in a superposition of different states until a measurement is made. For instance, when electrons pass through a barrier with two openings, they create an interference pattern on a detector, demonstrating that they were in a superposition of going through both openings at once. Schrödinger thought experiment takes this idea and extends it to a macroscopic object, a cat, in order to highlight how counterintuitive quantum mechanics can be when applied outside its usual domain. The paradox has sparked extensive discussions among scientists and philosophers about the interpretation of quantum mechanics. Some argue that the thought experiment shows that there is a problem with the way quantum mechanics is applied to large objects. Others propose that the paradox indicates the need for a deeper understanding of how observation affects a quantum system. Over the years, several interpretations of quantum mechanics have been developed to address these questions. While some interpretations suggest that the superposition persists until an observer intervenes, others propose that the process of decoherence, where interactions with the environment cause the superposition to break down, plays a crucial role in determining the outcome. One of the challenges in discussing Schrödinger cat is to separate the mathematical description from the intuitive picture. The mathematics of quantum mechanics allows us to calculate probabilities of different outcomes using a wave function. This wave function encompasses all the possibilities for the system. However, when it comes to everyday objects like a cat, our common sense view does not accommodate the idea of being in two states simultaneously. This contrast between the mathematical formalism and our intuitive understanding is what makes the paradox both fascinating and perplexing. In practical applications, quantum mechanics deals with these issues by focusing on systems where the effects of superposition can be directly observed, such as in experiments with individual atoms or photons. In these controlled settings, the predictions of quantum mechanics have been verified with high precision. The paradox serves as a reminder that when we try to extend these principles to larger, more complex systems, we encounter questions that challenge our basic assumptions about reality. Schrödinger cat paradox has also had implications for the development of quantum technologies. For example, in quantum computing, researchers work with systems that rely on the principles of superposition and entanglement to perform computations far more efficiently than classical computers. The idea that a quantum system can exist in multiple states simultaneously is what gives quantum computers their potential power. Similarly, in quantum cryptography, the delicate nature of quantum states is used to secure communication channels. Any attempt to measure the state of a quantum system in transit will disturb it, revealing the presence of an eavesdropper. While the cat in Schrödinger thought experiment is not meant to be taken literally, the experiment effectively illustrates how quantum mechanics forces us to rethink the concepts of measurement and reality at the microscopic level. The idea that a system can be in multiple states until it is observed is one of the most fundamental aspects of quantum theory. It shows that the act of observation plays a unique role, one that is absent from the deterministic predictions of classical physics. The next remarkable phenomenon is quantum entanglement, which occurs when two or more particles become linked in such a way that the state of one directly influences the state of the other, no matter how far apart they are. In simpler terms, imagine two particles that share a connection so deep that measuring one immediately tells you something about the other, even if they are separated by vast distances. To illustrate, picture a pair of gloves that have been separated into two boxes. If you open one box and find a left-hand glove, you instantly know that the glove in the other box must be a right-hand glove. In the quantum world, entangled particles share a similar kind of connection. However, unlike the gloves that always have a fixed identity, the properties of quantum particles are not determined until they are measured. Instead, entangled particles exist in a state where their properties are linked in a way that only becomes definite at the moment of measurement. Scientists have observed this phenomenon in a variety of experiments. For instance, when particles such as electrons or photons are created in pairs, they can become entangled in properties like spin or polarization. Once entangled, the particles remain connected regardless of the distance between them. If an experimenter measures a particular property of one particle, the result of that measurement instantly determines the corresponding property of its partner. One key aspect of entanglement is that it does not involve any direct signal or communication between the particles at the time of measurement. Instead, the connection is established at the moment the particles become entangled, and it persists as a fundamental feature of their shared state. This means that even if the particles are separated by large distances, the act of measuring one particle immediately reveals information about the other. This behavior has been confirmed in experiments where entangled particles were sent to detectors placed miles apart, yet their measurement outcomes were found to be correlated in a way that defies classical expectations. The curious nature of entanglement challenges our conventional understanding of how objects should behave. In everyday life, if two objects are separated, what happens to one should not instantly affect the other. With entangled particles, however, the results of measurements on one particle always match the expected outcomes for its partner. This mysterious link between particles, often referred to as spooky action at a distance, has puzzled scientists since it was first proposed and has led to intense research aimed at understanding the underlying mechanisms. In practical applications, the unique properties of quantum entanglement have opened the door to revolutionary technologies. One prominent example is quantum cryptography. In certain secure communication systems, entangled particles are used to generate encryption keys that are virtually impossible to intercept without detection. If an eavesdropper tries to measure the entangled particles during transmission, the disturbance introduced by the measurement immediately reveals the presence of interference, thereby alerting the communicating parties to a potential breach in security. Quantum entanglement also plays a vital role in the development of quantum computers. In these devices, entangled qubits work together to perform complex calculations that would be unmanageable for traditional computers. Because entangled qubits can represent multiple states at once and share information instantly, quantum computers have the potential to solve problems in areas such as cryptography, optimization, and simulation much more efficiently than classical computers. The phenomenon of entanglement is best understood by focusing on the experimental evidence that supports it. In one of the most famous experiments, a beam of light is passed through a crystal that splits it into two entangled photons. When these photons travel to separate detectors, measurements taken at each detector reveal outcomes that are closely linked. Even when the measurement settings are changed independently at each detector, the correlation between the outcomes persists. This experimental confirmation of entanglement has been repeated in many different setups, each time reinforcing the idea that particles can be deeply connected in ways that defy simple explanations. Another experiment involves sending entangled particles to detectors located far apart from each other. In these tests, researchers have carefully controlled the measurement settings and ensured that the particles are separated by distances that make any conventional communication between them impossible within the time frame of the experiment. Yet, when the results are compared, the outcomes are found to be correlated far beyond what would be expected if the particles were acting independently. These findings have been instrumental in shaping our modern understanding of quantum mechanics and have spurred further research into the nature of quantum connections. It is important to note that quantum entanglement does not imply that information or energy is being transferred faster than the speed of light. Instead, the correlations are a result of the shared quantum state established at the time of entanglement. This means that while the measurement outcomes are connected, they do not allow for any form of communication or signaling that would violate the established limits of relativity. The concept is more about the inherent structure of the quantum state rather than a transmission of signals between particles. Moreover, the persistence of entanglement over long distances has practical implications for the field of quantum networking. Researchers are working on ways to use entangled particles to create secure communication links and even to develop a quantum internet where information is transferred using the principles of quantum mechanics. Such networks could enable new levels of security and efficiency in data transmission, further demonstrating the transformative potential of quantum entanglement. In laboratory settings, entanglement is typically generated through processes such as spontaneous parametric down conversion, where a high-energy photon is converted into a pair of lower-energy entangled photons. The resulting entangled pairs are then carefully manipulated and measured to explore their properties. Over time, these experiments have not only confirmed the predictions of quantum mechanics, but have also helped refine our techniques for generating, controlling, and detecting entangled particles. The next striking perspective is the many worlds interpretation, which suggests that when a quantum event occurs, the universe splits into separate branches, each representing one of the possible outcomes. In everyday experience, when we perform an action, we expect one clear result. However, in the quantum realm, every possible outcome of a measurement can occur, but in separate, non-interacting branches of the universe. To explain this concept in everyday terms, imagine a scenario where a decision point leads to different routes. Think of standing at a fork in a quiet road. At that moment, one path leads to a peaceful countryside, while another leads to a bustling town. In our usual experience, you choose one path, and only that one becomes your reality. In the many worlds interpretation, when a quantum event occurs, the universe splits so that all the outcomes exist simultaneously in separate branches. In one branch, the decision might lead to the countryside. In another, it leads to the town. No branch is more real than the other. They simply coexist as parts of a much larger branching reality. At the heart of this interpretation is the idea that the quantum wave function never actually collapses to a single outcome. In other interpretations of quantum mechanics, a measurement forces the wave function to choose one definite state out of many possibilities. Many worlds, however, holds that the wave function continues to evolve without interruption. Every time a measurement is made, the universe divides, and each possible outcome happens in its own branch. This means that the seemingly random results we see are not a result of chance or collapse. They are simply the branch of the universe that we experience. To illustrate this with a common example, consider an experiment with a particle that can hit one of two detectors. In the conventional view, before the particle is detected, it exists in a superposition of hitting both detectors. When the measurement occurs, the superposition appears to collapse, and the particle is found at one detector. In the many worlds interpretation, no collapse occurs. Instead, the universe splits into two branches. In one branch, the particle is detected by the first detector, and in the other branch, it is detected by the second detector. Both outcomes exist, but observers in each branch experience only one of them. This approach provides a clear solution to the so-called measurement problem in quantum mechanics. The measurement problem arises because the mathematical description of quantum systems allows for a superposition of states, but when we perform a measurement, we only ever see one definite outcome. Many worlds resolves this by saying that every possible outcome is realized, each in its own separate branch of the universe. In this picture, there is no mysterious collapse of the wave function. The evolution of the wave function is always smooth and continuous. One of the remarkable aspects of the many worlds interpretation is its deterministic nature. The evolution of the wave function is governed by clear, well-defined laws, and there is no element of randomness introduced by measurement. Instead, the appearance of randomness arises because observers in any given branch are unaware of the other branches. Every possible outcome is determined by the initial conditions of the quantum system and the evolution dictated by quantum laws, but the observer's experience is limited to one branch, which gives the impression of a random choice. In practice, this interpretation suggests that every time a quantum event with multiple possible outcomes occurs, whether it is a particle passing through a barrier or a photon encountering a beam splitter, the universe splits. Over time, these splits add up to a vast number of parallel branches, each representing a different outcome of countless quantum events. The term many worlds reflects this immense branching structure, where the total number of branches could be unimaginably large, covering all the possibilities allowed by quantum mechanics. This perspective has significant implications for understanding quantum phenomena. For example, consider the famous double-slit experiment. When particles such as electrons are fired at a barrier with two slits, an interference pattern is observed on a screen, indicating that each electron appears to pass through both slits at once. In the many worlds view, the electron does not split its path or interfere with itself in a mysterious way. Instead, the electron passes through one slit in one branch of the universe and through the other slit in another branch. The overall interference pattern results from the collective effect of the branching structure, even though each individual branch shows the electron taking a definite path. The idea of branching universes also plays a role in modern technologies that rely on quantum mechanics. For instance, quantum computing leverages the principle of superposition and, by extension, the concept of branching possibilities. Qubits, the basic units of quantum information, can exist in multiple states at once. This allows quantum computers to process many possibilities simultaneously. Although the many worlds interpretation is one way to conceptualize this behavior, the practical workings of quantum computers rely on the underlying mathematics of superposition and interference. Many worlds also provides a way to understand entangled systems. When two particles become entangled, their states are linked in such a way that the outcome of a measurement on one particle is correlated with the outcome on the other, regardless of the distance between them. In the many worlds framework, the entangled particles are part of a single unified wave function that branches into different outcomes during measurement. Each branch reflects a consistent pair of outcomes that maintain the correlation predicted by quantum mechanics. While the idea of a continuously branching universe may seem extravagant, it is important to note that the many worlds interpretation is consistent with all the experimental evidence that supports quantum mechanics. It offers a way to view quantum phenomena without the need to invoke a special mechanism for wave function collapse. All the evolution of the system is described by the same mathematical laws, and the branching into different outcomes is a natural consequence of these laws. One of the challenges for the many worlds interpretation is that the additional branches of the universe are not directly observable. Observers are confined to their own branch, and there is no known way to interact with or detect the other branches. However, this does not detract from the internal consistency of the interpretation. Instead, it shifts the focus to how we understand the quantum system as a whole, a system that in principle contains every possible outcome of every quantum event. The next alternative perspective is the pilot wave theory, also known as the de Broglie-Bohm theory, which provides a different picture of how particles behave in the quantum world. In this view, particles always have a definite position and move along a clear, well-defined path. Unlike the more commonly discussed idea that particles exist in a blend of possibilities until they are measured, this theory asserts that each particle's location is fixed at all times. What makes the theory unique is the role of a guiding wave, which influences the particle's motion. Imagine a small boat navigating a flowing river. Although the boat follows a specific route determined by the river's current, the water itself flows broadly and covers a wide area. In the same way, a particle moves along a specific trajectory, but its motion is directed by a pilot wave that spreads out over space. This wave carries information about all the possible paths the particle might take, and through its influence, it gently steers the particle along one definite route. According to pilot wave theory, when a particle is not being observed, it does not exist as a fuzzy cloud of possibilities. Instead, its position is always well determined, even if we might not know it exactly. The wave that guides the particle evolves in time according to the same rules that govern other quantum systems, while the particle itself follows a path determined by the shape and features of this wave. In practical terms, if you were able to trace the movement of a particle under this theory, you would see a clear continuous line, a trajectory that the particle follows, rather than a series of jumps or sudden appearances. One of the classic experiments in quantum physics is the double-slit experiment, where particles like electrons produce an interference pattern that suggests they travel through both slits simultaneously. Pilot wave theory explains this in an intuitive way. In this experiment, the particle goes through one slit while its pilot wave passes through both. The waves emerging from the two slits then overlap and interfere with each other. This interference pattern shapes the way the pilot wave guides the particle, leading it to land in a location that, when many particles are observed, produces the familiar pattern of light and dark bands. Thus, even though each electron has a definite path, the overall pattern reflects the wave's influence as it experiences interference. In this framework, there is no need to invoke a mysterious collapse of a wave function when a measurement is made. The particle always has a specific position, and a measurement simply reveals where the particle is along its predetermined trajectory. The apparent randomness that we observe in experiments comes from our practical inability to know the exact details of the guiding wave and the particle's starting conditions. In other words, if we had complete knowledge of all the factors at work, we could, in principle, predict the exact path of the particle. However, because we are limited in what we can measure, outcomes appear probabilistic, even though the underlying process is completely deterministic. This deterministic aspect of pilot wave theory contrasts with other interpretations of quantum mechanics, where randomness is considered a fundamental property of nature. Here, every particle follows a precise continuous path, guided by a wave that evolves smoothly over time. The randomness we encounter in experiments is not built into the particle's behavior, but is due to the practical limitations in our ability to measure the complex details of the system. Over the years, pilot wave theory has been developed to ensure it makes the same predictions as standard quantum mechanics. Despite being an alternative way of looking at quantum behavior, it agrees with all experimental results. The theory explains not only the interference patterns seen in the double-slit experiment, but also other phenomena like quantum tunneling and entanglement, by describing how particles move under the influence of their pilot waves. For example, in quantum tunneling, particles are sometimes observed on the other side of a barrier that, according to classical physics, they should not be able to overcome. Within pilot wave theory, the guiding wave extends into the barrier, even if the particle itself does not have enough energy to climb over it. This extension of the wave means that there is a small chance the particle can be guided through the barrier, appearing on the other side. In this way, the theory offers a clear picture of how such processes occur without requiring the particle to jump in a way that defies classical intuition. Another practical area where pilot wave theory provides insights is in the realm of quantum computing. While quantum computers typically rely on the concept of superposition and interference, the deterministic trajectories described by pilot wave theory offer an alternative way of conceptualizing how qubits might be controlled and manipulated. Although the technology does not depend on one interpretation over another, having multiple ways to understand the underlying behavior can sometimes inspire new methods of control and error correction. It is important to note that while pilot wave theory introduces the idea of a guiding wave, this wave is not directly observed. Instead, its existence is inferred from the way particles behave in experiments. The theory provides a consistent and coherent way to explain quantum phenomena without the need for a sudden collapse of the wave function. Every measurement simply uncovers the particle's predetermined location along its path. This approach helps to sidestep some of the conceptual challenges found in interpretations that rely on the idea of wave function collapse. Critics of pilot wave theory point out that introducing the pilot wave adds an extra element that is not found in the standard formulation of quantum mechanics. However, proponents argue that this extra element helps to create a clearer, more intuitive picture of how particles move and interact. By assuming that particles always have definite positions, the theory allows for a more straightforward understanding of the processes involved in measurement and evolution. The next fascinating phenomenon is quantum tunneling, where particles pass through barriers that in classical physics would be completely insurmountable. In everyday experience, if an object, like a ball, lacks sufficient energy, it simply cannot overcome a wall. It bounces back, yet in the quantum realm, particles behave differently. Particles in quantum mechanics are described by a wave that represents a range of possible locations rather than a single point. When such a wave encounters a barrier, it does not stop abruptly at the edge. Instead, it gradually fades as it penetrates the barrier. This means there is a small chance that part of the wave reaches beyond the barrier, giving the particle the possibility of appearing on the other side, even if it seemingly lacks the energy to climb over. Imagine a scenario with a thin, flexible barrier, like a slightly permeable membrane. Although most of a ball's energy might not be enough to push through, there is a tiny chance, thanks to the ball's spread-out nature in the quantum picture, that it can be detected on the far side. This probability of tunneling through the barrier is not due to imperfections in our measurement, but rather is an intrinsic aspect of how particles behave at very small scales. The effect of quantum tunneling is seen in many physical processes. One notable example is radioactive decay, where particles confined within an atomic nucleus sometimes escape by tunneling through an energy barrier created by nuclear forces. Even though the particles do not have the classical energy required to break free, the tunneling effect enables them to appear outside the nucleus, which leads to the gradual process of radioactive decay. In the realm of modern technology, quantum tunneling plays a critical role. Consider scanning tunneling microscopes, STMs, devices that can image surfaces at the atomic level. In an STM, a very sharp tip is brought extremely close to a surface. Electrons can tunnel between the tip and the surface, creating a measurable current. By carefully scanning the tip over the surface and recording the variations in this tunneling current, scientists can produce detailed images that reveal the arrangement of individual atoms. Tunnel diodes, another application, are semiconductor devices that utilize the tunneling effect for fast switching. In these devices, electrons tunnel through a thin insulating layer between two conductors, allowing the diode to switch between different electrical states with remarkable speed. This property is highly valuable in high-frequency electronics and signal processing. Quantum tunneling also underpins the operation of flash memory. In these memory cells, electrons are transferred by tunneling to or from a small floating gate. This process enables the storage and erasure of data in a controlled and reliable manner, forming the basis for the non-volatile memory used in many modern electronic devices. The probability of tunneling is influenced by the characteristics of the barrier, its thickness and height, as well as by the properties of the particle itself. A thicker or taller barrier reduces the chance of tunneling, while a thinner or lower barrier increases it. This means that even for barriers that appear substantial, there remains a small but non-zero chance for a particle to appear on the other side. Quantum tunneling is a direct consequence of the wave-like nature of particles. In classical physics, objects are seen as solid and well-defined, but in the quantum picture, every particle has an associated wave that describes the probability of finding it at different locations. When this wave encounters a barrier, it extends into the region beyond, albeit with diminishing strength. When a measurement is made, there is a chance that the particle is found on the far side of the barrier, even though classical physics would have predicted it to be stopped. This phenomenon has been extensively confirmed by experiments. For example, when electrons pass through a thin insulating barrier between two conducting materials, a measurable current flows due to tunneling. Such experiments have consistently verified that particles can indeed cross barriers in ways that defy classical expectations. Quantum tunneling is also significant in chemical reactions, particularly at very low temperatures. In some reactions, particles tunnel through energy barriers, allowing the reaction to proceed even when the available energy would be insufficient under classical conditions. This tunneling effect can influence reaction rates and is important in fields ranging from astrochemistry to the design of new catalysts. The controlled use of quantum tunneling has led to breakthroughs in various technological fields. Engineers design devices at very small scales by taking advantage of tunneling, ensuring that electronic components work reliably even when classical ideas about energy barriers no longer hold. As technology continues to miniaturize, the effects of quantum tunneling become increasingly significant, driving further innovations in electronics and computing. Another crucial phenomenon is decoherence, which describes the process by which the strange behavior of quantum systems gradually transitions into the predictable behavior we observe in everyday life. At the quantum level, particles and systems can exist in a delicate state where they simultaneously display a range of possibilities, a kind of overlapping of different states that allows for interference effects. However, when these quantum systems interact with their surroundings, these subtle features start to disappear. This process, known as decoherence, essentially explains how quantum behavior transforms into classical behavior. Imagine a small quantum system, like an electron or a group of atoms, isolated in a perfectly controlled environment. In this isolated state, the system can maintain its quantum characteristics, such as being in a superposition of different states. The interference between these overlapping states is what gives quantum mechanics its unique and non-intuitive features. However, in any realistic situation, a quantum system is never completely isolated. It is constantly interacting with its environment. Air molecules, stray electromagnetic fields, and even the slightest vibrations can all play a role. These interactions are like a gentle but persistent noise that the quantum system experiences. Each interaction slightly alters the quantum state, gradually spreading out the information contained in the system into the environment. As the system becomes entangled with so many environmental factors, its quantum coherence, the ability to exhibit clear interference between different states, begins to dissolve. In practical terms, the well-defined interference patterns that characterize quantum behavior become blurred and eventually vanish. To illustrate, consider a very simple scenario, a tiny particle in a superposed state, where it could be in either of two places at once. If this particle were completely isolated, it might display interference effects, much like overlapping ripples on a pond. However, once the particle starts interacting with external particles or fields, these interactions measure or disturb its state. The result is that the superposed state effectively breaks apart into a mixture of states. Instead of being in a clear quantum superposition, the particle behaves as if it has settled into one of the possible positions. Its quantum spread is no longer observable. This gradual loss of interference does not happen abruptly. Instead, decoherence is a continuous process where the system's information is leaked into its surroundings. Over time, the system transitions from being described by a single coherent wave function to being described by a statistical mixture of states. In this mixed state, the distinct quantum effects are no longer apparent, and the system begins to behave according to the laws of classical physics. One way to think about decoherence is by imagining a delicate, detailed painting. When the painting is viewed up close under controlled lighting, every brushstroke and color blend is visible and contributes to the overall image. Now imagine gradually stepping back or introducing a filter that blurs the details. As the details fade, the image loses its fine structure, and what remains is a simpler, more uniform picture. Similarly, decoherence blurs the detailed quantum information contained in a system, making the distinct quantum interference effects fade away until only the average classical behavior remains. The process of decoherence plays a key role in understanding why we do not see quantum superpositions in our everyday world. In a laboratory, scientists can sometimes maintain quantum coherence by isolating systems very carefully, cooling them to extremely low temperatures or using vacuum chambers to minimize interactions. Under these conditions, quantum effects like superposition and entanglement can be observed and even harnessed for practical purposes such as in quantum computing. However, in everyday conditions, where interactions with the environment are inevitable, decoherence acts quickly to suppress these quantum effects. In the field of quantum computing, for instance, decoherence is both a challenge and a guiding principle. Quantum computers rely on maintaining coherent superpositions of states to perform complex calculations that classical computers cannot. However, Interactions with the environment, such as thermal vibrations or electromagnetic disturbances, can cause the delicate quantum states in a quantum computer to decohere, leading to errors in computation. Much of the research in quantum computing is focused on developing techniques to minimize decoherence, such as error correction protocols or using materials and designs that better isolate quantum bits from their surroundings. Another area where decoherence is crucial is in understanding the transition between the quantum and classical worlds. While quantum mechanics accurately describes the behavior of tiny particles, the macroscopic objects we interact with every day follow the rules of classical physics. Decoherence provides the bridge between these two realms by showing how the detailed quantum information becomes smeared out when a system is not perfectly isolated. It explains why a baseball, for example, is always found in a specific location even though, in principle, it is made up of particles that could be in a superposition of states. The constant interaction with the environment causes any potential quantum interference to vanish long before the baseball is observed. Experiments designed to study decoherence often involve creating controlled quantum systems and then deliberately introducing interactions with an environment. Researchers have observed that as these interactions increase, the quantum coherence diminishes in a predictable way. This experimental evidence supports the idea that decoherence is a natural process dictated by the fundamental interactions between a system and its surroundings. Decoherence also helps clarify the role of measurement in quantum mechanics. In traditional interpretations, the act of measurement is associated with a sudden collapse of the quantum state into a single outcome. With decoherence, the apparent collapse is understood as the natural result of a system becoming entangled with its environment. Once the information about the system is dispersed into the surrounding environment, it is effectively impossible to observe the original quantum interference. Thus, the transition from quantum to classical behavior happens without needing to invoke any mysterious collapse mechanism. It is simply the result of unavoidable interactions. In practical terms, this understanding of decoherence has far-reaching implications. Engineers designing quantum devices must account for decoherence to ensure that the devices function correctly. Similarly, the concept of decoherence informs the way scientists interpret experiments at the smallest scales, guiding the development of theories that reconcile quantum behavior with classical observations. Another fundamental framework is quantum field theory, which unifies our understanding of particles and forces into one elegant picture. Imagine space not as an empty void, but as a vast, continuous fabric filled with fields that stretch out in every direction. In this picture, what we think of as particles, like electrons, photons, or quarks, are not tiny little objects traveling through space. Instead, they are like ripples or disturbances in these all-pervasive fields. To get a clearer picture, think of a calm pond. The surface of the water is smooth and continuous, representing one of these fields that fills space. Now, imagine tossing a pebble into the pond. The pebble creates ripples that travel outward across the water. In quantum field theory, these ripples are analogous to particles. The pebble itself is not what we're looking at. Instead, we see the wave patterns it creates on the surface. In this way, particles are simply excitations in the underlying field. This idea transforms our view of the universe. Instead of considering particles as isolated, tiny billiard balls, quantum field theory tells us that every particle is a local vibration in a field that exists everywhere. When two particles interact, what is really happening is that their fields are interacting. The forces between particles are simply the result of the way these fields push, pull, or exchange energy with one another. For example, take light. In traditional thinking, light is made of particles called photons, but in quantum field theory, the electromagnetic field is the fundamental entity. Photons are the ripples or excitations in this electromagnetic field. When you see light, what you are observing is the manifestation of a disturbance traveling through a field that exists throughout the universe. One of the most exciting aspects of quantum field theory is that it is the foundation of the Standard Model, the theory that describes the known fundamental particles and their interactions. The Standard Model explains how particles interact through forces like electromagnetism, the weak nuclear force, and the strong nuclear force. In this framework, each type of particle is linked to its own field. Electrons, quarks, and even the Higgs boson are all different excitations in their corresponding fields. Interactions between these particles are described as exchanges of energy between their fields. When two particles come close to one another, their fields overlap and interact, resulting in forces that we can observe as attraction or repulsion. To understand these interactions without getting lost in technical details, imagine two people standing in a crowded room. Each person has their own personal space, like a field surrounding them. When they move close to each other, their personal spaces overlap. Depending on the nature of their interaction, they might gently push against each other or share a moment of connection. In quantum field theory, particles behave in a similar manner. Their fields overlap and interact, and this interaction can result in the exchange of energy or the transformation of one type of particle into another. Quantum field theory also provides a natural explanation for phenomena such as the creation and annihilation of particles. In classical physics, particles are thought of as fixed entities that exist until they decay. However, in the quantum picture, particles can spontaneously appear and disappear. These processes occur all the time, especially in very energetic environments. They are seen as fluctuations in the fields. For instance, in high-energy collisions, the energy from the interaction can create new particles, ripples in the field that were not there before. Conversely, when particles meet, they can cancel each other out, causing the ripples to subside. This ability for fields to continuously produce and absorb excitations is a core idea that unifies our understanding of particle physics. Another fascinating aspect of quantum field theory is the concept of virtual particles. In the quantum realm, the fields are never completely at rest. Even in a perfect vacuum, there is always a tiny amount of activity. This is because the fields are subject to constant fluctuations. These fleeting excitations, known as virtual particles, appear and disappear in extremely short periods. They are not directly observable in the same way as real particles, but their effects can be measured indirectly. For example, the force between two electrically charged particles is influenced by these virtual particles, which mediate the force. This process is what gives rise to the familiar electromagnetic force that governs interactions between charged objects. In everyday terms, quantum field theory is like a grand tapestry where every thread represents a field. The particles are the patterns woven into this fabric, and their interactions are the result of how these threads pull on each other. When you look at the tapestry as a whole, you see a unified picture of the universe where all phenomena are connected through the interplay of these fields. It is a picture that has been incredibly successful in predicting experimental results and deepening our understanding of nature. Despite its abstract nature, quantum field theory has practical implications. It has enabled the development of technologies like semiconductors and lasers, which are based on the principles of how particles and fields interact. Moreover, research in this field continues to push the boundaries of our understanding, potentially leading to breakthroughs in areas such as quantum computing and even in our quest for a unified theory that marries quantum mechanics with gravity. One of the challenges in grasping quantum field theory is that it requires us to abandon some of our classical intuitions. In our everyday experiences, we think of objects as distinct and unchanging. Quantum field theory, on the other hand, invites us to consider that at the most fundamental level, the universe is a dynamic interplay of fields, with particles emerging as temporary disturbances. This shift in perspective has been one of the most profound developments in modern physics, reshaping our understanding of the building blocks of reality. Experimental evidence supporting quantum field theory is abundant. Particle accelerators, such as those at major research facilities, smash particles together at high speeds, creating a host of new particles. The patterns and interactions observed in these experiments match the predictions made by quantum field theory remarkably well. These experiments have not only confirmed the existence of many predicted particles, but have also helped scientists refine their models of how the fields interact and evolve. Another intriguing concept is the quantum vacuum, which challenges our everyday notion of empty space and reveals a seething background of virtual particles and energy fluctuations. When we think of a vacuum, we imagine a complete absence of matter, a void with nothing in it. However, in the realm of quantum physics, the vacuum is far from empty. Instead, it is a dynamic stage where fluctuations and fleeting disturbances constantly occur, even in what appears to be complete nothingness. At the heart of this idea is the understanding that space itself is filled with quantum fields. These fields exist everywhere, and particles are simply temporary excitations or ripples in these fields. In the case of the quantum vacuum, these fields are in their lowest possible energy state, but this state is not static. Because of the inherent properties of quantum mechanics, even the lowest energy state is subject to random minute fluctuations. This means that, rather than being a silent void, the vacuum is like a quiet, continuous pulse, a subtle background hum of activity. One of the most striking manifestations of this activity is the appearance and disappearance of what are called virtual particles. These are particles that seem to pop into existence for an extremely brief moment before vanishing again. They are not particles in the conventional sense that can be directly observed, but their effects can be measured. The idea is that the energy present in the vacuum allows these temporary particles to form and then quickly annihilate each other, contributing to a fluctuating, lively background. A well-known phenomenon that provides evidence for the reality of the quantum vacuum is the Casimir effect. When two uncharged, parallel plates are placed very close together in a vacuum, they experience an attractive force that is not predicted by classical physics. This force arises because the quantum fluctuations of the fields between the plates are slightly different from those outside, creating a small pressure difference that pushes the plates together. The Casimir effect is one of the tangible pieces of evidence that even empty space is teeming with quantum activity. The vacuum in quantum field theory is sometimes described as having a zero-point energy, meaning that even when a system is at its lowest energy state, there is still an irreducible amount of energy present. This energy is not due to any particles moving around in a classical sense, rather it is a fundamental property of the quantum fields themselves. It is this energy that gives rise to the fluctuations we observe, making the vacuum a dynamic and active environment rather than a featureless void. In practical terms, the quantum vacuum has significant implications for our understanding of the universe. For instance, the fluctuations in the vacuum are believed to have played a role in the early moments of the universe, influencing the distribution of matter and the formation of large-scale structures. These tiny fluctuations, magnified over billions of years, helped shape the cosmos we see today. Although these ideas are deeply rooted in complex mathematics and theoretical physics, the core concept remains accessible. What appears to be empty space is actually filled with a restless, subtle energy that underlies all physical phenomena. The idea of a seething quantum vacuum also changes how we think about the nature of nothingness. In classical physics, nothingness is truly empty, a place devoid of matter and energy. Quantum physics, however, tells us that even in the absence of particles, the fields that permeate space are never completely at rest. They are always fluctuating, always in motion. This leads to a richer, more nuanced picture of the universe, where even the void has its own character and behavior. These insights have practical consequences in the field of technology as well. In some advanced electronic devices, engineers must account for the effects of vacuum fluctuations. For example, in certain highly sensitive measurements, the noise generated by these quantum fluctuations can become significant. Researchers are continually exploring ways to understand and control these effects, which might lead to improvements in precision measurement technologies and other applications where quantum effects are critical. Moreover, the concept of the quantum vacuum has sparked interesting questions about the fundamental limits of energy extraction. The idea that empty space is filled with energy, even if it is the lowest possible form, has led to theoretical discussions about whether this energy could someday be harnessed in some way. While practical applications of such ideas remain speculative, they continue to inspire research into the deeper nature of the universe and the limits of what is physically possible. It is also worth noting that the quantum vacuum is a central element in many modern theories of physics. Quantum field theory, for instance, relies on the idea that all particles are excitations in underlying fields that exist throughout space. The vacuum state of these fields is what we refer to as the quantum vacuum. In this view, the properties of particles and forces are all related to the behavior of these fields in their lowest energy state, with the fluctuations of the vacuum playing a crucial role in determining the interactions between particles. When we observe phenomena, such as the spontaneous emission of light or the behavior of electrons in semiconductors, we are often seeing the influence of the quantum vacuum. The fluctuations provide the background against which all quantum processes occur, setting the stage for the creation, interaction, and annihilation of particles. This constant quiet activity gives the universe a kind of rhythm, a pulse of energy that persists even in the most seemingly empty regions of space. Another fundamental principle is time symmetry in quantum mechanics, which states that the fundamental rules governing particle behavior remain the same, whether time moves forward or backward. In other words, if you were to reverse the flow of time, the equations that describe a quantum system would still hold true. This concept may seem counterintuitive because in our everyday experience, events appear to unfold in only one direction, from past to future. But at the quantum level, the laws of physics do not inherently favor one direction of time over the other. Imagine watching a video of a billiard game. In the video, you see balls colliding, ricocheting off each other, and following clear trajectories across the table. Now picture playing that video in reverse. In the reversed video, the balls still follow smooth, continuous paths. Their motions obey the same physical rules as in the forward version. The striking point is that the equations governing the motion of the balls do not change whether the game is played forward or backward. Similarly, the fundamental equations in quantum mechanics have this built-in symmetry with respect to time. At the quantum level, particles are described by wave functions, which contain all the information about a system's possible behaviors. These wave functions evolve over time according to rules that are time reversal symmetric. This means that if you were to rewind the process described by a wave function, the evolution would follow the same patterns as if time were moving forward. In simple terms, the mathematical description of a quantum system does not distinguish between past and future in the way that our everyday experience does. To illustrate this with a more familiar analogy, imagine a perfectly still pond on a calm day. If you drop a pebble into the pond, ripples spread out evenly in all directions. Now think about what would happen if you could reverse the process, if the ripples could somehow converge back into the pebble. In the world of quantum physics, many processes are similar in that the laws governing them work just as well if the ripples were to move in reverse. The idea is that the underlying rules remain the same, regardless of the direction in which time is considered. This time symmetry becomes especially interesting when we look at certain quantum processes. In many quantum experiments, the outcomes are determined by probabilities rather than certainties. However, the evolution of the wave function that describes these probabilities is smooth and predictable, regardless of whether time is moving forward or backward. The equations that tell us how the system evolves do not have a built-in arrow of time. They do not inherently say this is the past or this is the future. Instead, they simply describe a continuous process that can be mathematically reversed. One area where time symmetry is particularly notable is in the study of particle interactions. In a particle collision experiment, for instance, the behavior of particles before and after a collision can be described by the same underlying principles. If you could capture the entire collision process and then reverse it, the system would evolve in the same way, with the roles of incoming and outgoing particles swapped. This illustrates that, at least in theory, the laws of quantum mechanics do not prefer a direction for time. They work equally well whether time is flowing forward or backward. It is important to note, however, that while the equations themselves are time-symmetric, the act of measurement in quantum mechanics introduces an element that seems to break this symmetry. When a measurement is made, a quantum system that is described by a range of possibilities is observed to be in one specific state. This collapse of the wave function appears to favor one outcome, and in doing so, it gives us the impression that time has a preferred direction, specifically that it moves from a state of multiple possibilities to one definite outcome. Despite this apparent asymmetry during measurement, many physicists believe that the underlying dynamics remain time-symmetric. The measurement process itself is still an area of active research and debate. The implications of time symmetry extend into various technological and scientific fields. In quantum computing, for example, understanding the time evolution of quantum states is essential for designing algorithms and error correction methods. Because the evolution of quantum states is governed by time-symmetric equations, researchers can exploit this property to better control and manipulate quantum systems. This control is crucial for performing computations that rely on the delicate interference patterns produced by quantum states. Time symmetry also plays a role in the study of fundamental interactions in nature. When scientists investigate the forces that govern particle behavior, they often work under the assumption that the underlying laws are time reversal invariant. This assumption simplifies many calculations and helps to unify different aspects of physical theory. In high-energy physics experiments, where particles are accelerated and collided at incredible speeds, the fact that the governing laws are time-symmetric allows researchers to draw conclusions about processes that occurred both before and after the collision. Another practical aspect of time symmetry is its role in simulations of quantum systems. Researchers often use computer models to predict how a quantum system will evolve over time. Since the fundamental equations do not distinguish between past and future, these simulations can be run backwards as well as forwards, providing a powerful tool for testing theories and exploring new phenomena. This flexibility is one of the reasons why time symmetry is such a valuable concept in theoretical physics. Another fundamental concept is quantum information, which represents the way nature stores and processes data at the tiniest scales. In our everyday world, information is something we encounter all the time in the form of text on a page, images on a screen, or signals transmitted by our smartphones. In the quantum realm, however, information takes on an entirely different character, governed by the peculiar rules of quantum mechanics. At the heart of quantum information is the idea that particles like electrons or photons are described by quantum states. These states encode information about the particle's properties, such as its position, momentum, or spin. Unlike classical bits, which can be either 0 or 1, quantum bits, known as qubits, can exist in a combination of both states simultaneously. This is a direct result of the principle of superposition, where a qubit holds a blend of possibilities until it is measured. Imagine a light switch that can be both on and off at the same time until someone checks it. In the quantum world, a qubit is like that switch, existing in a state that is a mixture of 0 and 1. It is only when we interact with the system, when a measurement is made, that the qubit chooses a specific state. This ability to be in multiple states at once allows quantum systems to process a vast amount of information in ways that classical systems cannot match. Quantum information is not just about individual qubits. It also encompasses the interactions between qubits, which can lead to complex correlations that have no counterpart in classical physics. One striking example is quantum entanglement, where the states of two or more qubits become so deeply linked that the state of one instantly reflects the state of the other, regardless of the distance separating them. These correlations enable quantum systems to perform tasks such as secure communication and high-speed computation with a level of efficiency that would be impossible using classical information. In the language of quantum information, the evolution of a quantum system is governed by precise mathematical rules. These rules allow scientists to predict how a system will change over time and how information is transferred between particles. In a way, quantum information is like the code that underpins the behavior of everything at the microscopic level. It tells us not only what a particle is doing, but also how it might interact with other particles, how it can be manipulated, and how its state can be used to perform work. One of the practical applications of quantum information is in the field of quantum computing. Unlike classical computers, which use bits that can be either 0 or 1, quantum computers use qubits that can be in superpositions of states. This means that a quantum computer can process many different possibilities simultaneously. In certain types of problems, such as factoring large numbers or simulating complex molecules, this ability allows quantum computers to solve problems much faster than classical machines. Another key application is quantum cryptography, which leverages the principles of quantum information to secure communications. In quantum cryptography, information is encoded in quantum states. Any attempt to eavesdrop on these states disturbs them, which can be detected by the communicating parties. This makes quantum cryptography exceptionally secure and has the potential to revolutionize the way sensitive data is transmitted. The field of quantum information also extends to quantum error correction. Because quantum systems are very sensitive to their environment, information stored in qubits can easily become corrupted by interactions with external noise. Researchers have developed sophisticated methods to detect and correct these errors, ensuring that quantum information can be preserved and manipulated reliably over time. This is crucial for the development of practical quantum technologies. Another intriguing aspect of quantum information is its role in understanding fundamental physics. Over the past few decades, scientists have begun to view the laws of physics through the lens of information theory. In this perspective, information is not merely a tool for describing systems, it is seen as a core component of physical reality itself. This approach has led to new insights into topics such as black hole thermodynamics, where the information content of a black hole appears to be related to its surface area rather than its volume. The interplay between quantum information and gravity is an active area of research. Some theories propose that the structure of space and time could emerge from more fundamental quantum informational processes. This line of inquiry is part of a broader effort to reconcile quantum mechanics with general relativity, and it suggests that the fabric of the universe may be woven from quantum bits of information. Experimental research in quantum information has produced remarkable results. Laboratories around the world have succeeded in creating entangled pairs of particles, manipulating qubits with high precision, and even demonstrating basic quantum algorithms on small-scale quantum computers. These experiments not only confirm the theoretical predictions of quantum mechanics, but also pave the way for future technologies that could harness the power of quantum information. One of the central challenges in the field is maintaining coherence in quantum systems. Because quantum states are delicate, they can easily lose their information through interactions with the environment, a process known as decoherence. Researchers work hard to isolate quantum systems and develop error correction techniques to protect the information encoded within them. The struggle to preserve quantum coherence is at the heart of ongoing efforts to build reliable quantum computers and communication networks. The next groundbreaking field is quantum gravity, which seeks to merge two of the most successful theories in physics, quantum mechanics, which governs the very small, and general relativity, which explains gravity on a cosmic scale. Although each theory has been incredibly successful in its own domain, they have long remained separate, leading scientists to search for a way to bring them together into a single, unified description of the universe. Imagine the universe as a vast, intricate fabric. On one hand, general relativity describes this fabric as a smooth, continuous expanse that bends and curves in the presence of mass and energy. This bending is what we experience as gravity, shaping the orbits of planets, the formation of stars, and even the dynamics of entire galaxies. On the other hand, quantum mechanics tells us that at the smallest scales, inside atoms and particles, the universe is far from smooth. It is instead a world of discrete, fluctuating phenomena, where particles can exist in several states at once, and where probabilities dictate behavior rather than absolute certainties. The challenge of quantum gravity lies in reconciling these two pictures. At everyday scales, the effects of quantum mechanics are typically negligible, and general relativity provides an excellent description of gravitational forces. However, when we examine extreme environments, such as the heart of a black hole or the conditions that prevailed just after the Big Bang, the rules of both theories become important. In these realms, the smooth curvature of spacetime described by general relativity meets the unpredictable granular world of quantum mechanics, and our current theories seem to clash. One of the main goals of quantum gravity is to create a framework where gravity itself is described using quantum principles. This means that rather than treating gravity as a continuous field that curves spacetime, scientists aim to understand it as emerging from more fundamental quantized elements. These elements would be the building blocks of spacetime itself, similar to how particles are the building blocks of matter. There are several approaches that researchers are exploring to develop a theory of quantum gravity. Two of the most well-known are string theory and loop quantum gravity. Although these theories take very different routes, they share the common goal of bridging the gap between the cosmic and the quantum. String theory proposes that the fundamental constituents of the universe are not point-like particles, but rather tiny vibrating strings. Each vibration of the string corresponds to a different particle, much like different notes played on a musical instrument. In this view, gravity emerges naturally from the vibrations of closed strings that move through a higher dimensional space. The theory provides a way to unite all forces of nature into one framework. However, it also introduces complex ideas, such as extra dimensions, which have yet to be directly observed, and remains an area of active research and debate. Loop quantum gravity takes a different approach by focusing directly on the geometry of spacetime. In this theory, spacetime is not a continuous entity, but is composed of discrete chunks, much like a mosaic made up of tiny tiles. These tiles of spacetime are extremely small, on the order of the Planck length, which is many orders of magnitude smaller than anything we can currently observe. In loop quantum gravity, the smooth fabric of spacetime is seen as an approximation that emerges when many of these discrete elements come together. This theory provides a way to describe how the gravitational field behaves at very small scales and has led to interesting predictions about the nature of black holes and the early universe. Both string theory and loop quantum gravity illustrate that our classical picture of spacetime breaks down when quantum effects become significant. At these scales, the familiar notion of a smooth, continuous space no longer applies. Instead, the very structure of spacetime may be subject to quantum fluctuations, tiny temporary changes in its fabric that occur even in what we consider empty space. Understanding these fluctuations is key to unlocking the secrets of the universe's most extreme conditions. Quantum gravity also has profound implications for our understanding of black holes. In the realm of classical physics, black holes are regions of space where gravity is so strong that nothing, not even light, can escape. However, when quantum effects are taken into account, black holes are predicted to have a temperature and to slowly emit radiation, a phenomenon known as Hawking radiation. This prediction arises from considering the quantum behavior of particles near the event horizon, the boundary of a black hole, A proper theory of quantum gravity is expected to provide a more complete description of black holes, explaining how they form, evolve, and ultimately how they might evaporate over time. Furthermore, the quest for quantum gravity is intimately connected with our understanding of the universe's origins. The Big Bang, the event that marked the beginning of the cosmos, is a situation where both quantum effects and gravity are important. Near the very start, the energy densities and temperatures were so high that the quantum nature of space-time could not be ignored. A successful theory of quantum gravity would help to explain the conditions of the early universe and might even shed light on what happened before the Big Bang, a question that remains one of the biggest mysteries in physics. While a complete and experimentally confirmed theory of quantum gravity remains elusive, the ongoing research in this field is already yielding valuable insights. Experimental tools like gravitational wave detectors and high-energy particle accelerators are pushing the boundaries of what we can observe, offering clues about the quantum aspects of gravity. These observations help to refine theoretical models and guide researchers toward a deeper understanding of how the smallest scales of quantum mechanics are connected to the largest scales of the cosmos. Developments in quantum gravity are not only significant for theoretical physics but also hold potential for future technologies. Although practical applications may be far off, the underlying principles could one day lead to breakthroughs in how we manipulate space and time at a fundamental level. For example, a better grasp of quantum gravity might pave the way for new methods of information processing or lead to advances in materials science, where the properties of matter are determined by the interplay of quantum effects and gravitational interactions. Quantum Zeno effect. The pause in the flow of time. Imagine watching a pot of water on the stove, waiting for it to boil. In everyday life, time flows naturally and continuously, and events proceed without interruption. However, in the strange realm of quantum physics, there exists a phenomenon that seems to slow down or even halt the evolution of a system simply by observing it repeatedly. This is known as the quantum Zeno effect. To understand this concept, start by picturing a delicate, tiny particle that can be in several states at once, a hallmark of the quantum world. Normally, if left undisturbed, the particle's state would evolve gradually over time, exploring its many possibilities. Now imagine that you keep checking on this particle very frequently. Remarkably, if you observe it often enough, you can prevent it from changing its state at all. It's as if the act of observation itself freezes the system in place. Consider a simple analogy. Think of a light that is set to slowly change color over time. If you glance at it occasionally, you might see it transitioning from one hue to another. But if you keep looking at it constantly, the light may seem to hold on to its current color much longer than expected. In the quantum world, a similar effect occurs. The very act of measuring the particle repeatedly interferes with its natural evolution, keeping it locked in its initial state. This is why the effect is sometimes described as the pause in the flow of time. The name quantum Zeno effect is inspired by an ancient Greek philosopher Zeno of Elea, who is famous for his paradoxes about motion. One of Zeno's paradoxes suggests that if you continuously check on a moving arrow, it might appear motionless at each instant, leading to the puzzling idea that motion is an illusion. In a similar vein, the quantum Zeno effect shows that by frequently checking a quantum system, we can seemingly stop its evolution, just as Zeno's arrow appears frozen in mid-air when observed in a series of snapshots. To put it simply, when a quantum system is measured, it is forced to reveal a specific outcome from the many possibilities contained in its state. If measurements are taken very frequently, the system is repeatedly forced to restart from the same state, preventing it from evolving naturally into another state. In other words, the system doesn't get the chance to progress because every observation resets its state, much like repeatedly pressing a pause button on a video. It is important to understand that the quantum Zeno effect is not a result of poor measurement techniques or errors in our instruments. Rather, it is a fundamental property of quantum systems. The process of measurement in quantum mechanics is unique. It is not just a passive observation but an active interaction that changes the state of the system. When you measure a quantum system, you are not simply reading off a pre-existing value, you are influencing the system in such a way that it chooses a particular outcome. If these measurements happen very quickly in succession, the system is repeatedly forced to make the same choice over and over, effectively locking it in place. One way to visualize this is to imagine a delicate spinning top that is gradually beginning to wobble and change direction. If you were to look at it continuously, you might be able to influence its motion, keeping it spinning steadily without changing its orientation much. Although the analogy isn't perfect, it gives a sense of how constant observation can stabilize a system that would otherwise evolve. This phenomenon has been observed in various experiments. For example, in certain setups, scientists have managed to slow down the decay of unstable quantum states simply by measuring them frequently. Under normal circumstances, an unstable state might change or decay rapidly, but with constant observation, the decay process is suppressed, and the state persists longer than expected. This experimental verification of the quantum Zeno effect confirms that the act of observation in the quantum world can have a very real impact on how systems evolve. Another striking example is found in experiments with atoms trapped by laser beams. In these experiments, atoms are prepared in a particular quantum state and then subjected to a series of rapid measurements. Researchers have found that the atoms remain in their initial state for much longer periods than they would if they were not being measured so frequently. The outcome is a clear demonstration of how continuous observation can effectively freeze the evolution of a quantum state. The implications of the quantum Zeno effect extend beyond pure science. They also have potential applications in the development of quantum technologies. In quantum computing, for instance, maintaining the coherence of quantum bits, or qubits, is essential for performing calculations. Unwanted interactions with the environment can cause qubits to lose their delicate quantum states, a problem known as decoherence. By carefully controlling the frequency and timing of measurements, it may be possible to use the quantum Zeno effect to help preserve the state of qubits for longer periods, thereby enhancing the performance and reliability of quantum computers. Similarly, in the field of quantum control, the quantum Zeno effect can be used to stabilize quantum systems. By designing protocols that involve rapid, repeated measurements, scientists can keep a quantum system in a desired state, which could be valuable for precision measurements and other sensitive experiments. It is also interesting to note that while the quantum Zeno effect appears to freeze a system, there is a complementary phenomenon known as the anti-Zeno effect. In certain conditions, frequent measurements can actually accelerate the evolution or decay of a quantum system. The balance between these two effects depends on the details of the system and the nature of the interactions involved. This duality adds an extra layer of complexity to our understanding of quantum dynamics, showing that observation can have different outcomes depending on the context. In essence, the quantum Zeno effect offers a fascinating insight into the interplay between measurement and evolution in the quantum world. It highlights the unique role that observation plays in quantum mechanics, not merely as a means of gathering information, but as an active process that can dictate the behavior of a system. By repeatedly pausing the natural evolution of a quantum state through rapid measurement, the effect challenges our intuitive notions of time and change at the microscopic level. To summarize, the quantum Zeno effect reveals that by observing a quantum system frequently, we can effectively freeze its state, preventing it from evolving naturally. This effect arises from the inherent properties of quantum mechanics, where measurement is not a passive process but one that actively shapes the state of the system. Experiments have demonstrated that rapid, repeated measurements can slow down or even halt processes that would normally occur in an unobserved quantum system. The implications of this effect are far-reaching, offering potential benefits in the fields of quantum computing, quantum control, and precision measurement. Ultimately, the quantum Zeno effect deepens our understanding of the dynamic relationship between observation and evolution in the quantum realm, challenging our everyday perceptions of time and change. Quantum contextuality, layers beyond the obvious. Imagine you're looking at a beautiful, multifaceted gemstone. Depending on the angle and the lighting, the gem reveals different colors and patterns. No single color fully captures its beauty. Instead, its appearance shifts based on how you choose to observe it. In quantum mechanics, a similar idea applies to the properties of particles. Quantum contextuality tells us that the outcome of a measurement on a quantum system can depend on other measurements performed alongside it. In other words, the result you get for one property is not just an intrinsic quality of the particle, it also depends on the context of what else is being measured. To break this down in everyday terms, think about a simple object like a smartphone. When you use your phone, its performance and behavior depend on several settings: screen brightness, volume, network connection, and more. Changing one setting can affect how the phone operates overall. Similarly, in quantum physics, when you try to measure a property of a particle, the result may depend on the full experimental setup, the complete set of measurements being carried out. This means that a particle does not have a fixed independent property that exists regardless of how you observe it. Instead, what you observe can change based on the other properties you decide to measure at the same time. This idea contrasts sharply with our everyday expectations from classical physics, where objects are thought to have well-defined properties regardless of observation. For example, if you measure the temperature of a cup of coffee, the reading you obtain is independent of whether you also check its color or its volume. The coffee has a definite temperature, independent of other observations. In the quantum realm, however, things work differently. The measurement of one property can influence or be influenced by the measurement of another. The outcome is not solely a property of the particle, but rather it emerges from the entire experimental context. One way to understand this is to imagine an artist painting a picture. The final artwork is not just a product of individual colors applied in isolation. It is a harmonious composition where each color and brushstroke influences the overall image. In quantum contextuality, the image of a particle's property is formed only when it is observed within the full composition of the experiment. Changing one element of the composition, say the lighting or the angle from which you view the painting, can alter the perception of the colors and details in the artwork. Similarly, altering the set of measurements in a quantum experiment can lead to different outcomes for the same property. Experiments in quantum mechanics have provided clear evidence of contextuality. In certain tests, particles are measured under different sets of conditions, and the results vary in ways that cannot be explained if the particles had predetermined properties. This means that the act of measurement itself plays a crucial role in determining what is observed. The properties of quantum systems are not fixed until the full context of the measurement is taken into account. To put it simply, quantum contextuality challenges the idea that the attributes of a particle exist independently of observation. Instead, these attributes are revealed only when measured, and the outcome can vary depending on which other measurements are performed simultaneously. The context of the experiment, the full array of measurements and settings, shapes the result. It's as if the particle holds a variety of potential characteristics, and only a specific combination of observations brings one of these characteristics to the forefront. Another way to think about this is to imagine a jigsaw puzzle. Each piece of the puzzle contains part of the overall picture, but you cannot fully understand the image by looking at one piece alone. The meaning of each piece depends on how it fits with the others. In a similar manner, the properties of a quantum particle are interdependent. They make sense only when you consider the entire experimental setup. Changing the arrangement of the pieces, altering the context, can change the picture that emerges. Quantum contextuality also has important implications for quantum computing and other technologies. In quantum computing, qubits are used to store and process information. The way qubits behave can depend on the context of the quantum operations performed on them. This interdependence can be harnessed to perform complex computations that classical computers struggle with. However, it also means that designing and controlling quantum systems requires a deep understanding of how different operations interact with one another. Recognizing the contextual nature of quantum properties is key to developing effective algorithms and error correction techniques in quantum computing. Furthermore, the phenomenon of quantum contextuality has spurred new theoretical frameworks. Researchers are working to understand how the context-dependent behavior of quantum systems might lead to a more unified understanding of quantum mechanics. By examining how different measurements interact, scientists hope to uncover deeper principles that govern the quantum world. This research could eventually lead to a clearer picture of why the quantum realm behaves so differently from our everyday experiences. In addition to technological applications, quantum contextuality also offers insights into the fundamental nature of reality at the microscopic level. It underscores that quantum systems are not simply collections of independent properties, but rather they are deeply interwoven with the measurement process. This realization forces us to reconsider how information is encoded in the fabric of the quantum world. The outcomes of measurements are not just passive reflections of pre-existing properties, they are actively shaped by the broader experimental context. Imagine a scenario in which a scientist is trying to measure the spin of an electron, a property that can be thought of as the electron's intrinsic angular momentum. In classical terms, one might expect that the electron's spin would have a definite value regardless of how it is measured. However, experiments show that the result depends on the entire measurement setup. If the spin is measured along one axis, a certain value is observed. But if the measurement is performed along a different axis, the outcome can differ. This dependence on the measurement context is a hallmark of quantum contextuality and illustrates how quantum systems defy classical expectations. The experimental validation of quantum contextuality comes from a variety of setups where researchers have carefully designed tests to isolate the contextual nature of quantum systems. These experiments consistently demonstrate that the values obtained in quantum measurements cannot be explained by assuming that particles carry predetermined independent properties. Instead, the data reveal that the outcomes are inseparable from the conditions under which the measurements are made. Quantum phase transitions, the silent shift of states. Imagine a world where changes occur not with heat or movement, but through subtle, almost imperceptible shifts at the very foundation of matter. In our everyday experience, we see water freezing into ice or boiling into steam as temperatures change. These are classical phase transitions, where heat acts as the driving force behind a dramatic transformation. Now picture a transition that happens not because of temperature, but purely because of quantum mechanics, a silent shift in the state of a material that takes place at absolute zero temperature. This is what we call a quantum phase transition. In a typical phase transition, like the melting of ice, energy in the form of heat causes the molecules to rearrange themselves. However, at the extreme low end of the temperature scale, when thermal energy is almost non-existent, quantum mechanics takes over. Here the behavior of particles is governed not by the agitation of heat, but by the principles of quantum mechanics. Even at absolute zero, where you would expect everything to be completely still, particles continue to exhibit quantum fluctuations, tiny restless movements that can lead to sudden changes in the state of the system. Quantum phase transitions occur when a material changes its state due to a variation in an external parameter, such as pressure, magnetic field, or chemical composition, rather than temperature. Imagine a delicate balance where the material is perched on the edge of two different states. As you tweak this external parameter ever so slightly, the material can shift from one state to another. This transition is silent in the sense that it doesn't come with the familiar signals of heat or light. Instead, it happens deep within the material's quantum structure. To illustrate this concept, think about a collection of tiny magnets in a solid material. At low temperatures, these magnets might align in a particular pattern, creating a state known as magnetic order. However, by gradually increasing the strength of an external magnetic field, you might force these magnets to rearrange themselves into a different configuration. In a classical phase transition, you might observe a sudden change in properties such as conductivity or magnetization. In a quantum phase transition, this change happens even at temperatures where thermal energy is virtually absent, driven solely by the underlying quantum mechanics of the system. One way to picture this is by imagining a calm lake that is perfectly still on a winter day. Underneath the frozen surface, however, there may be subtle currents and shifts in the water's structure that you can't see with the naked eye. These hidden currents represent the quantum fluctuations in the material. As you gradually alter an external condition, say by slightly increasing the pressure, the hidden currents can rearrange, leading to a sudden change in the overall structure of the lake beneath the ice. The surface might remain frozen, but the internal configuration has shifted in a way that alters the properties of the entire system. In many quantum materials, these transitions are associated with dramatic changes in behavior. For example, certain materials known as quantum magnets can switch from being magnetically ordered to disordered as the strength of an applied magnetic field is varied. This transition can change how the material conducts electricity or how it responds to external forces. Even though these changes occur at temperatures near absolute zero, their effects can be significant, offering insights into the fundamental nature of matter. Quantum phase transitions are also important because they provide a window into the behavior of systems that are too complex to understand using classical ideas alone. In classical phase transitions, we can often predict what will happen based on the energy involved and the interactions between particles. However, in quantum phase transitions, the rules are different. The changes are driven by quantum fluctuations, and the system can exist in a superposition of states until the transition is complete. This means that near the transition point, the material can exhibit properties that are a blend of both phases, a phenomenon that has intrigued researchers for many years. Another interesting aspect of quantum phase transitions is how they can lead to the emergence of entirely new states of matter. In some cases, when a material undergoes a quantum phase transition, it enters a phase that has no classical counterpart. These exotic states can display unusual properties such as superconductivity, where electrical resistance vanishes, or topological order, where the material's properties are protected by its geometric structure rather than by symmetry. These new phases are not just scientific curiosities, they have practical implications for technology, particularly in the fields of quantum computing and materials science. The study of quantum phase transitions also challenges our understanding of how phase transitions occur. In classical systems, the transition is typically smooth or abrupt, based on changes in thermal energy. In quantum systems, the transition can be far more complex, with the possibility of gradual crossovers or abrupt shifts that depend on the delicate interplay of quantum forces. Researchers use advanced techniques, both experimental and theoretical, to probe these transitions. For example, by cooling materials to ultra-low temperatures and applying precisely controlled external fields, scientists can observe the onset of a quantum phase transition and measure how the properties of the material change. One experimental approach involves using neutron scattering or magnetic resonance techniques to study the behavior of atoms in a quantum material. These methods allow researchers to detect changes in the arrangement of particles and to observe the fluctuations that signal an impending phase transition. The data gathered from these experiments not only confirm the presence of a quantum phase transition but also help to refine theoretical models that describe these complex processes. From a practical standpoint, understanding quantum phase transitions is key to developing new materials with tailored properties. Materials that undergo quantum phase transitions can be engineered to have specific responses to external stimuli, such as changes in magnetic field or pressure. This ability to control material properties at the quantum level opens up exciting possibilities for designing sensors, quantum computers, and other advanced technologies that rely on precise control of matter. In summary, Quantum phase transitions represent a silent shift in the state of matter driven by quantum fluctuations rather than by thermal energy. These transitions occur at extremely low temperatures, where classical ideas of phase change no longer apply, and the behavior of the material is determined by the subtle interplay of quantum forces. By gradually altering an external parameter such as pressure or magnetic field, a material can transition from one state to another, revealing new and sometimes exotic properties. The study of these transitions not only deepens our understanding of the quantum world, but also has practical implications for the development of new technologies and materials. It shows us that even in the quiet, near absolute zero conditions, the quantum world is dynamic and full of surprises, with each silent shift of state offering new insights into the nature of matter. Transitioning now to the concept of quantum chaos, the gentle disorder in the microscopic realm, let's explore how order and disorder intertwine at the smallest scales. In our everyday experience, we associate chaos with complete disorder, like a turbulent storm or a crowded room where nothing seems to follow a pattern. However, when it comes to the microscopic world, chaos takes on a gentler, more subtle form. Quantum chaos is the study of how quantum systems, which are governed by precise mathematical rules, can exhibit behavior that appears unpredictable or disordered under certain conditions. Imagine a beautifully arranged mosaic where each piece is carefully placed to form an intricate picture. Now, picture what might happen if a few pieces were slightly shifted or rotated. The overall image might still be recognizable, but there would be unexpected patterns emerging, and subtle irregularities would start to play a role. This gentle departure from perfect order is akin to what happens in quantum chaos. In the quantum realm, particles and systems follow strict, well-defined laws. For example, when we describe an electron in an atom, quantum mechanics tells us exactly how the electron's probability distribution is shaped. Yet, when we start looking at more complex systems, such as atoms interacting in a molecule or electrons moving in a disordered material, things become more complicated. Even though the fundamental rules remain unchanged, the collective behavior of many interacting particles can lead to patterns that are difficult to predict with complete certainty. This emergence of intricate sensitive behavior from simple rules is what we call quantum chaos. One way to visualize quantum chaos is to think of a calm lake that, when disturbed by a stone, forms ripples that eventually interfere with one another. If the ripples are gentle and well organized, the lake may settle into a smooth pattern. But if the ripples are created in quick succession or from multiple disturbances, the patterns can become complex and seemingly random. In a similar way, even if a quantum system is governed by deterministic laws, the interactions among its parts can create outcomes that seem chaotic. A key feature of quantum chaos is its sensitivity to initial conditions. In everyday life, this sensitivity might remind us of a game of billiards, where a tiny difference in the angle of a shot can lead to dramatically different outcomes. In quantum systems, small variations in the initial state of a system can lead to significant differences in its later behavior. Even though the evolution of the system is governed by precise mathematical equations, predicting the exact outcome can become extremely challenging because of this inherent sensitivity. Another aspect of quantum chaos is the way it bridges the gap between classical chaos and quantum mechanics. In classical physics, chaos is well understood in systems like weather patterns, where small uncertainties in measurement can lead to vastly different future states. In the quantum world, the rules of chaos are a bit different because quantum systems can exist in a superposition of states, and their behavior is described by probabilities rather than certainties. Despite these differences, there is a growing understanding that the disorder we see in quantum systems can be linked to classical chaos when the system becomes large enough or interacts with its environment. Scientists study quantum chaos by looking at various systems where these effects are pronounced. One common example is the behavior of electrons in a quantum dot, a tiny confined region that acts much like an artificial atom. In these systems, the paths that electrons can take are influenced by both quantum rules and subtle interactions with the surrounding material. As a result, the energy levels of the electrons and the patterns of their movement can display irregularities that are characteristic of chaos. These patterns, while not completely random, show a degree of disorder that reflects the sensitive dependence on the system's initial state. Another experimental approach involves studying the vibrations of atoms in small clusters or molecules. When the atoms in a molecule interact, their collective motion can be described by quantum mechanics. However, if the interactions are complex enough, the resulting vibrational patterns can appear disordered, much like the unpredictable ripples in our disturbed lake. These studies help scientists understand how chaos emerges from quantum interactions and how it affects the properties of materials. Quantum chaos is not just a theoretical curiosity, it has practical implications as well. In fields like quantum computing, understanding how chaotic behavior can emerge in a system is crucial for designing stable devices. Quantum computers rely on maintaining coherent quantum states for as long as possible, but even small amounts of chaos or disorder can lead to errors in computation. By studying quantum chaos, researchers can develop methods to predict, control, or mitigate these effects, leading to more reliable quantum technologies. Furthermore, the study of quantum chaos offers insights into fundamental questions about the nature of reality. It challenges the assumption that systems governed by precise laws must always behave in an orderly manner. Instead, even in the highly controlled quantum world, complex interactions can give rise to behavior that appears unpredictable. This realization has profound implications for our understanding of the universe, suggesting that order and disorder are not mutually exclusive but are intertwined aspects of the same underlying reality. One interesting area of research is how quantum chaos manifests in systems that are on the borderline between the quantum and classical worlds. As systems become larger and more complex, quantum effects start to fade and classical behavior begins to dominate, a process influenced by decoherence. In these transitional systems, remnants of quantum chaos can still be observed, providing a link between the two realms. Understanding this connection helps scientists bridge the gap between the predictable world of classical physics and the probabilistic nature of quantum mechanics. Researchers also use advanced mathematical tools and computer simulations to study quantum chaos. By modeling the behavior of quantum systems under different conditions, they can predict how small changes in initial conditions might lead to large variations in outcomes. These models not only help to explain experimental observations, but also guide the design of new experiments that probe the chaotic dynamics of quantum systems. In summary, quantum chaos, the gentle disorder in the microscopic realm, reveals that even though quantum systems are governed by precise laws, their interactions can lead to outcomes that appear complex and unpredictable. This phenomenon is characterized by a sensitive dependence on initial conditions and serves as a bridge between the orderly predictions of quantum mechanics and the disorder observed in classical chaotic systems. Through studies of systems like quantum dots, molecular vibrations, and transitional systems between the quantum and classical worlds, scientists are uncovering how chaos emerges from the delicate interplay of quantum rules. This understanding not only deepens our knowledge of fundamental physics, but also has practical applications in areas such as quantum computing, where controlling and mitigating chaotic effects is crucial for building reliable devices. Quantum chaos challenges our intuition, reminding us that even in the realm of the very small, disorder can arise in gentle, intricate ways, weaving a rich tapestry of behavior that continues to inspire and intrigue researchers around the world. Topological quantum states. The hidden geometry of matter. Imagine a beautiful mosaic or a stained glass window, where each piece fits together in a pattern that remains intact even if you chip or disturb a few fragments. This is the essence of what we call topological quantum states, a way to understand how the overall shape or geometry of a material can protect its unique properties. At its core, topological quantum states are about how certain materials exhibit behaviors that are not just determined by their chemical composition, but also by the global arrangement of their internal structure. In other words, it's the hidden geometry of matter that plays a crucial role. This hidden geometry isn't something you can see with the naked eye. It's encoded in the way electrons move and interact within the material, creating states that are remarkably robust. To illustrate, think about a donut and a coffee cup. Although these objects look very different at first glance, in the world of topology, a branch of mathematics that studies properties that remain unchanged under continuous deformations, they are considered the same. Both have one whole. This idea might seem surprising at first, but it shows us that sometimes the overall shape of something is what truly matters, rather than every small detail. In the context of quantum materials, certain states depend on this kind of global property. When electrons in a material organize themselves in a particular way, they can form what are known as topological states. These states are special because they are protected by the global geometry of the system. That means even if there are imperfections or disturbances, like impurities in the material or slight deformations, the topological state remains stable. One striking example of these ideas in action is found in topological insulators. Unlike ordinary insulators, which do not conduct electricity at all, topological insulators are materials that conduct electricity on their surfaces while remaining insulating in their bulk. The electrons on the surface move in a manner that is dictated by the overall geometry of the material. They are locked into place by the topological properties, making the surface conduction highly robust. Even if you scratch or bend the material, these conducting states persist, much like the enduring pattern in a well-crafted mosaic. Another fascinating phenomenon comes from the concept of edge states. In many topological materials, the unique behavior is not found in the interior of the material but at its boundaries. These edge states arise naturally because of the way the material's overall geometry forces the electrons to behave differently at the surface than in the bulk. Imagine a river flowing smoothly in the center but changing its characteristics near the banks due to the influence of the surrounding landscape. Similarly, the electrons near the edge of a topological material follow paths and rules that are distinct from those in the interior, leading to effects such as unidirectional conduction, where electrons can only travel in one direction along the edge. One of the most remarkable aspects of topological quantum states is their resilience. In many everyday systems, even a small defect or disturbance can dramatically alter the behavior of the system. In contrast, the properties of topological states are protected by the material's global structure. This means that they can withstand significant amounts of disorder or deformation without losing their unique characteristics. It's like having a secret code built into the very fabric of the material, a code that ensures its behavior remains consistent regardless of minor imperfections. This robustness has practical implications for technology. For example, topological quantum states are being explored as a promising route toward fault-tolerant quantum computing. In quantum computers, maintaining the delicate state of qubits, quantum bits, is a major challenge, as even small disturbances can cause errors. However, if qubits can be designed to take advantage of topological protection, they could become much more stable and resistant to noise. This could be a crucial step in building practical quantum computers that can perform complex calculations reliably. The journey to understanding topological quantum states has also led researchers to uncover entirely new phases of matter. Unlike traditional phases such as solid, liquid, or gas, these new phases arise purely from the quantum mechanical properties of the material. They often exhibit unusual and unexpected behaviors that cannot be explained by classical physics alone. For instance, some topological materials have been found to exhibit superconductivity, a state where electrical resistance drops to zero under conditions where conventional theories would not predict it. These discoveries not only broaden our knowledge of material properties, but also open up new avenues for creating innovative devices with novel functionalities. From a research perspective, scientists study these phenomena using advanced techniques that probe the electronic structure of materials. Experiments using angle-resolved photoemission spectroscopy or scanning tunneling microscopy have provided detailed images of the surface states in topological insulators, confirming the theoretical predictions. These experimental breakthroughs are helping to bridge the gap between abstract mathematical ideas and real-world materials, demonstrating that the hidden geometry of matter is not just a theoretical curiosity but a tangible aspect of nature. Moreover, the theoretical framework that underpins topological quantum states has evolved over the years. Researchers combine concepts from quantum mechanics, solid-state physics, and topology to build models that predict how electrons will behave in various materials. These models help guide the search for new topological materials and provide insight into how to manipulate their properties for technological applications. In summary, topological quantum states reveal that the behavior of electrons in certain materials is governed not just by local interactions, but by the overall hidden geometry of the material. Much like a mosaic or a stained glass window, where the beauty and resilience of the pattern depend on the arrangement of the pieces as a whole, topological states are protected by the global structure of the system. They give rise to remarkable phenomena such as surface conduction in topological insulators, robust edge states, and even novel phases of matter that challenge our classical understanding. Transitioning now to our next concept, let's explore quantum fluctuations, the subtle stir of the energy field. In the classical view of empty space, a vacuum is simply a void, a complete absence of matter and energy. However, quantum mechanics reveals that even the emptiest space is never truly empty. Instead, it is filled with tiny restless movements that occur continuously, even in what we consider to be a perfect vacuum. At the heart of this idea is the fact that, in quantum theory, particles are described by fields that permeate all of space. These fields are never completely at rest. Even when a field is in its lowest energy state, what scientists call the vacuum state, it still experiences fluctuations. These fluctuations are spontaneous, brief changes in the field that occur without any external trigger. They are a direct consequence of the uncertainty inherent in quantum mechanics, where energy and other properties are never exactly zero, even in the ground state. Imagine a calm, glassy lake on a windless day. At first glance, the surface appears perfectly still and tranquil. However, if you look closer, you might notice tiny ripples, small transient waves that briefly disturb the smooth surface before fading away. In the same way, the quantum vacuum is not a static emptiness, but a dynamic environment where fields are continuously in motion, creating momentary disturbances that we call quantum fluctuations. These fluctuations give rise to what are known as virtual particles. Virtual particles are temporary, short-lived excitations in a field. They momentarily pop into existence, exist for an extremely brief time, and then vanish again. Although they cannot be observed directly, their effects can be measured. For instance, the force between two uncharged parallel plates placed very close together, a phenomenon known as the Casimir effect, arises from differences in the quantum fluctuations inside and outside the gap between the plates. The tiny pressure exerted by these fluctuations causes the plates to attract each other, providing clear evidence that even empty space has a hidden active quality. Another way to picture quantum fluctuations is to think of the vacuum as a seething cauldron of energy. Even when there is no obvious energy present, the quantum fields are never completely quiet. Instead, they constantly generate and absorb these virtual particles, creating a background hum of activity. This constant activity is a natural part of the quantum world and is essential for understanding many physical phenomena. One practical consequence of quantum fluctuations can be seen in the behavior of atoms and molecules. Even in a cold, isolated system, these fluctuations can affect the energy levels of particles, causing small shifts in the observed spectra. These shifts are not due to any external forces, but are a direct result of the intrinsic quantum fluctuations in the vacuum. Such effects have been measured with remarkable precision in experiments, confirming the predictions made by quantum field theory. Quantum fluctuations also play a critical role in the early universe. In the moments following the Big Bang, the universe was incredibly small and dense, and quantum fluctuations were significant. These tiny fluctuations, amplified over time, eventually led to the formation of galaxies and large-scale structures in the cosmos. While this is a complex area of study, the core idea remains accessible. Even the most empty parts of space are lively and active due to quantum fluctuations, and these tiny disturbances can have far-reaching consequences. The study of quantum fluctuations is not only important for understanding the fundamental nature of reality, but it also has practical applications. For instance, in modern electronics, quantum fluctuations can influence the behavior of superconductors and other materials at very low temperatures. Engineers and scientists must take these effects into account when designing devices that operate on the quantum scale. The insights gained from studying quantum fluctuations help improve the performance of sensitive instruments like superconducting qubits in quantum computers, where even small fluctuations can lead to errors. Another area where quantum fluctuations are crucial is in precision measurement. In experiments that aim to measure physical constants or detect subtle forces, the background noise created by quantum fluctuations can become a limiting factor. Researchers work to minimize and control these fluctuations to achieve higher accuracy in their measurements. This ongoing effort is essential for the advancement of technologies that rely on precise control at the quantum level. Experimental methods to study quantum fluctuations have evolved significantly over the years. Techniques such as high-resolution spectroscopy, scanning tunneling microscopy, and measurements of the Casimir effect allow scientists to probe the vacuum state and observe the effects of these fleeting virtual particles. The data obtained from these experiments not only validate theoretical models, but also guide the development of new technologies that exploit the unique properties of quantum fluctuations. The concept of quantum fluctuations challenges the classical idea that a vacuum is completely empty. Instead, it reveals that the vacuum is a dynamic environment filled with transient activity that plays a crucial role in various physical processes. This active nature of the vacuum is one of the cornerstones of quantum field theory, shaping our understanding of forces and interactions at the smallest scales. Furthermore, quantum fluctuations are intimately connected with the phenomenon of zero-point energy, the idea that even at absolute zero temperature, systems retain a small amount of energy due to these intrinsic fluctuations. Zero-point energy is a key aspect of many quantum systems and has implications for both fundamental physics and potential technological applications. It reminds us that even in the absence of external energy, the quantum world remains active and vibrant. In summary, quantum fluctuations, the subtle stir of the energy field, reveals that what we traditionally think of as empty space is in fact a bustling arena of constant activity. Even in its lowest energy state, a quantum field is never completely at rest, but is continuously generating and absorbing temporary excitations known as virtual particles. These fluctuations are responsible for a range of observable effects, from the Casimir effect to small shifts in atomic energy levels, and they have played a significant role in shaping the universe from its earliest moments. By understanding quantum fluctuations, scientists are better equipped to design advanced technologies, from quantum computers to precision measurement devices that operate at the very limits of our physical world. This insight into the hidden activity of the vacuum not only deepens our understanding of quantum theory, but also provides a foundation for practical innovations that harness the subtle stir of the energy field. Quantum solitons, the stable ripples in a dynamic sea. Imagine standing by a quiet lake at dawn. The water is calm and smooth, yet every now and then you notice a ripple that travels across the surface without changing shape or losing its energy. In the quantum world, there exists a phenomenon that mirrors this behavior, a phenomenon called quantum solitons. In everyday life, we're used to waves that eventually disperse, fade, or interact with one another to form new patterns. For example, think about the ripples created when a stone is tossed into a pond. These ripples spread out, overlap, and gradually diminish as they move away from the point of impact. In many cases, the energy of the wave disperses into the surrounding water, and the pattern eventually fades into a gentle murmur. However, sometimes, under very special conditions, a wave can travel over long distances without changing its shape or losing energy. Such waves are called solitons. Quantum solitons are a similar concept but occur in quantum systems. In these systems, particles and fields are described by wave-like properties. A soliton in this context is a stable localized wave packet that behaves like a solitary ripple, traveling through a medium while maintaining its shape and energy. This stability is remarkable because, in a dynamic, ever-changing quantum sea, most wave packets would normally spread out or dissipate over time. Solitons, however, emerge as self-reinforcing entities that persist even when they interact with other disturbances. To visualize this, picture a long, narrow channel in a river where water flows steadily. Most of the time, small disturbances in the water quickly merge with the main current and lose their distinct identity. But occasionally, a particularly strong and well-formed wave can appear that travels down the channel without losing its form. This is the essence of a soliton, a self-contained, robust ripple in an otherwise dynamic environment. In quantum systems, solitons are created under specific conditions where the forces acting on the particles balance out the tendency of the wave packet to spread. This balance results in a stable solitary wave that can travel over long distances without altering its shape. The stability of quantum solitons makes them particularly interesting because they offer a window into how energy and information can be transported efficiently in a quantum medium. One of the key areas where quantum solitons have been observed is in optical fibers. In these fibers, light waves are used to transmit information over vast distances. Under certain conditions, the light can form solitons, stable pulses that maintain their shape even as they travel through the fiber. This property is extremely useful for communication technologies, as it means that the signal does not degrade over long distances, allowing for high-quality data transmission. The concept here is that the balance between dispersion, which would normally cause the light pulse to spread out, and the non-linear properties of the fiber creates a self-stabilizing pulse, a quantum soliton. Beyond optics, quantum solitons have been observed in other systems as well, such as in Bose-Einstein condensates. A Bose-Einstein condensate is a state of matter that occurs at temperatures near absolute zero, where a large number of atoms occupy the same quantum state, behaving as a single coherent entity. Under these extreme conditions, researchers have found that solitons can form within the condensate. These solitons appear as localized disturbances that travel through the condensate without dissipating, offering valuable insights into the behavior of matter at ultra-low temperatures. The stability of quantum solitons also has important implications for future technologies. For example, in the field of quantum computing, maintaining the integrity of quantum information over time is a significant challenge. Quantum solitons could potentially be used to transport information across quantum networks with minimal loss, thanks to their robust nature. Their ability to resist dispersion and maintain a fixed form means that they could serve as carriers of quantum information, preserving the delicate quantum states needed for computation. Moreover, the study of quantum solitons helps researchers understand the underlying balance of forces in quantum systems. In a typical quantum wave packet, two competing effects are at work. On one side, dispersion tends to spread the packet out over time, while on the other side, nonlinear interactions can focus and stabilize it. When these two effects are precisely balanced, a soliton emerges. This interplay is not only a fascinating aspect of quantum physics but also a practical one, as it can lead to new ways of controlling and manipulating quantum systems. In experimental settings, scientists create and observe quantum solitons by finely tuning the conditions in their laboratories. For instance, in optical experiments, by adjusting the intensity and wavelength of the laser light, researchers can create stable soliton pulses that travel through the fiber without changing shape. Similarly, in experiments with Bose-Einstein condensates, researchers use magnetic or optical traps to create conditions where solitons can form and be studied. These experiments provide concrete evidence that under the right circumstances, the quantum world can support stable solitary waves that behave in a remarkably predictable manner. Quantum solitons also illustrate the broader principle that even in the most dynamic and fluctuating environments, order can emerge. They remind us that the quantum realm, while often characterized by uncertainty and rapid change, is also capable of producing structures that are stable and long-lived. This duality between disorder and order is a recurring theme in quantum mechanics and is central to understanding how complex behaviors arise from simple underlying laws. In summary, quantum solitons represent stable, self-reinforcing wave packets that persist in dynamic quantum systems. They are the stable ripples that travel through a medium without dissipating, even when most wave-like disturbances would normally spread out or fade away. Found in systems ranging from optical fibers to Bose-Einstein condensates, these solitons illustrate the delicate balance between dispersion and nonlinearity in the quantum world. Their stability is not only a subject of fundamental scientific interest, but also holds promise for practical applications in quantum communication and computing. By studying quantum solitons, scientists are uncovering new ways to control the transport of energy and information in quantum systems, shedding light on how order can emerge from the inherent dynamism of the microscopic realm. This fascinating phenomenon underscores the remarkable and often surprising nature of quantum mechanics, where even in a sea of constant fluctuations, stable, coherent structures can arise and persist, guiding the flow of energy and information with quiet precision. Moving on to our next concept, let's explore quantum error correction, a set of ingenious techniques designed to protect the delicate quantum bits, or qubits, that form the foundation of quantum computing. In the quantum realm, qubits can exist in complex states where they hold a combination of values simultaneously. This remarkable ability is what gives quantum computers their potential power. However, qubits are also extremely sensitive to their surroundings. Even the smallest disturbance, such as stray electromagnetic noise or tiny vibrations, can disrupt their delicate state, causing errors that can jeopardize the entire computation. Imagine you have a priceless, intricate piece of artwork made of fragile materials. Every time you transport it, there's a risk of damage. To safeguard this masterpiece, you might create several high-quality copies or install advanced protective measures. Quantum error correction works in a similar way for qubits. It provides a strategy to detect and correct errors without directly measuring and disturbing the qubit's delicate quantum state. At the heart of quantum computing is the ability of qubits to be in superposition, a blend of multiple states at once. This property allows quantum computers to process a vast number of possibilities simultaneously. Yet with such power comes a significant challenge. The quantum states are prone to error. In a classical computer, errors can often be corrected by simply checking and copying bits multiple times. But in a quantum computer, directly measuring a qubit to check for errors would collapse its superposition, essentially destroying the very advantage that makes quantum computing so promising. So how can we protect quantum information without disturbing it? The answer lies in a clever approach that uses redundancy and indirect measurement. Instead of storing information in a single qubit, quantum error correction encodes the information into a carefully designed set of multiple qubits. Think of it as writing your important data, not on a single sheet of paper, but on several layers of overlapping, interwoven sheets. If one sheet gets smudged or torn, the overall message can still be recovered from the other layers. One common method of quantum error correction involves using what are known as quantum error correcting codes. These codes work by spreading the information of a single qubit over several physical qubits in such a way that if a small error occurs in one or a few of them, the error can be detected and corrected by comparing the outcomes across the group. It's a bit like having multiple backup copies of your data that work together to check for inconsistencies. However, the challenge here is that any direct measurement could ruin the superposition state, so the process has to be designed to extract error information indirectly. Consider an analogy. Imagine you're writing a secret message on a delicate, invisible piece of paper that can easily fade or be smudged. To ensure your message isn't lost, you might encode it in a way that spreads the information across several different sections of a more robust medium. Later, even if parts of the message are damaged, you can reconstruct the original message by comparing the different sections. Quantum error correction uses similar principles, but instead of physical damage, it deals with the noise or unwanted interactions that can alter the quantum state of a qubit. Another aspect of quantum error correction is the concept of syndrome measurement. This process involves measuring certain properties of the qubits in the error-correcting code, not the information itself, but indicators of whether an error has occurred. These measurements provide a syndrome or a set of clues that tells you which qubits might have been affected. Importantly, these syndrome measurements are designed to leave the underlying quantum information intact. Once an error is detected, a correction operation is applied to restore the qubits to their intended state. For instance, imagine you have a row of lights that should all be on. If one light flickers off, a sensor detects the anomaly without directly interfering with the lights. The system then triggers a mechanism that turns the light back on, restoring the row to its proper state. In quantum error correction, the sensors are the syndrome measurements, and the corrective actions are the operations applied to fix the error. This process happens very quickly and seamlessly, often without any noticeable interruption to the overall computation. Quantum error correction is not merely a theoretical concept, it has practical implications for building real quantum computers. As quantum processors become more complex and involve larger numbers of qubits, the impact of errors becomes more pronounced. Researchers are actively developing and refining error correction protocols to ensure that quantum computations can be carried out reliably, even in the presence of noise and imperfections. In many experimental setups, scientists have demonstrated basic quantum error correction by encoding a single logical qubit into several physical qubits and successfully correcting errors that occurred during computation. This capability is crucial because even a tiny error can propagate through a quantum circuit and lead to incorrect results. By incorporating robust error correction, quantum computers can, in principle, perform long and complicated calculations without being derailed by the inherent fragility of qubits. This is one of the key reasons why quantum error correction is often seen as the backbone of future quantum computing technology. Another important area of research involves finding new, more efficient error correction codes. The goal is to minimize the number of extra qubits required to protect the information, as every additional qubit adds complexity and potential sources of error. Researchers are exploring various strategies, from topological error-correcting codes, which use the geometry of qubit arrangements to provide inherent protection, to concatenated codes, where layers of error correction are applied hierarchically. Each of these approaches offers unique advantages and challenges, and the quest for optimal error correction is a vibrant field of study. Furthermore, quantum error correction has implications beyond computing. It helps deepen our understanding of how quantum information can be preserved and transmitted. In quantum communication, for example, maintaining the integrity of information over long distances is a major challenge. Error correction protocols are essential for ensuring that quantum keys and other forms of quantum data can be sent securely from one location to another without degradation. In summary, quantum error correction is the set of techniques that safeguard fragile qubits from the ever-present disturbances of the environment. By encoding quantum information across multiple qubits and using indirect measurements to detect and correct errors, this approach allows quantum computers and communication systems to function reliably despite the inherent sensitivity of quantum states. Like layered backups for critical data, quantum error correction ensures that even if a few qubits are affected by noise, the overall information remains intact. This is vital for the future of quantum technologies, as it provides the necessary stability for practical applications such as complex quantum computations and secure quantum communications. Through ongoing research and innovative engineering, scientists are steadily advancing our ability to control and correct quantum information, moving us closer to realizing the full potential of the quantum revolution. Now, let's move on to quantum simulation, a powerful tool that lets us reflect aspects of the quantum world on a digital canvas. Imagine being able to create a miniature controllable version of a complex system on a computer, where you can test and explore behaviors that are otherwise too difficult to observe directly. Quantum simulation is much like that. It is the art of replicating the behavior of a quantum system within another, more accessible quantum system, allowing us to study and understand its properties in a controlled environment. Consider a painter working on a digital tablet. Instead of using traditional paints, the artist uses software to mix colors and create images that mimic reality. The digital canvas can be manipulated, zoomed in on, and altered in ways that a physical canvas might not allow. Similarly, quantum simulation creates a digital representation of a quantum system, a model that reflects the behavior of particles, fields, and interactions on a smaller, more manageable scale. This simulation becomes a kind of virtual laboratory where scientists can experiment with and observe phenomena that are too subtle or complex to study directly in nature. One of the major challenges in understanding the quantum world is that many quantum systems are incredibly complex. Whether it's the behavior of electrons in a high-temperature superconductor or the intricate interactions within a large molecule, the sheer number of particles and their possible states make direct analysis extremely difficult. With quantum simulation, scientists can recreate these systems in a simplified form, isolating key features and studying them one at a time. It's like taking a high-resolution photograph of a bustling city and then zooming in on a single street to analyze the patterns and interactions in detail. In practice, quantum simulation often involves using one well-controlled quantum system to mimic another. For example, researchers might use ultra-cold atoms trapped in a specially designed lattice created by laser beams. This arrangement can serve as a model for the behavior of electrons in a crystal. By adjusting the parameters of the optical lattice, much like adjusting the settings on a digital art program, scientists can simulate different conditions, such as changing the strength of interactions between particles or the geometry of the system. This method allows them to observe how these adjustments affect the overall behavior, offering insights into phenomena like superconductivity or magnetism. Another example comes from the field of quantum chemistry. Molecules are quantum systems with complex interactions that determine their chemical properties. Simulating these interactions on a classical computer is notoriously challenging due to the exponential increase in complexity as molecules grow larger. Quantum simulators, however, have the potential to model these interactions more naturally by directly encoding the quantum information into a controllable system. This could lead to more accurate predictions of chemical reactions, paving the way for breakthroughs in drug discovery and materials science. Quantum simulation also plays a vital role in bridging the gap between theory and experiment. The mathematical equations of quantum mechanics are powerful, but solving them for complex systems is often impractical. With quantum simulation, theoretical models can be tested experimentally in a controlled setting. This is similar to how a digital prototype can be used to test design ideas before creating a physical product. The simulation acts as a proof of concept, allowing researchers to see if their theories hold up under real-world conditions and to refine their models based on experimental observations. One of the most exciting prospects of quantum simulation is its ability to explore systems that are inherently quantum in nature. For example, certain exotic states of matter, states that arise only due to quantum effects, can be challenging to study directly because they occur only under extreme conditions. By using quantum simulators, scientists can recreate these states at more accessible temperatures and pressures, making it possible to study their properties and behavior in detail. This not only deepens our understanding of the quantum world, but may also lead to practical applications in technology, such as the development of new, more efficient electronic devices or novel materials with unique properties. Furthermore, quantum simulation is also a stepping stone towards fully functional quantum computers. While classical computers struggle to simulate quantum systems due to their inherent complexity, quantum simulators leverage the same principles that make quantum computers so powerful. In essence, a quantum simulator is a special-purpose quantum computer designed to solve specific problems in quantum mechanics. As research progresses, these simulators are expected to handle larger and more complex systems, gradually paving the way for universal quantum computing. Another appealing aspect of quantum simulation is its flexibility. Just as an artist can adjust the colors, brushes, and techniques on a digital canvas to create a desired image, scientists can tweak the parameters of a quantum simulator to model different scenarios. This adjustability allows for a wide range of experiments, from testing fundamental questions about the nature of quantum entanglement to exploring the behavior of particles in novel materials. The ability to dial in different conditions and directly observe the outcomes is a powerful advantage, offering a level of control and precision that is hard to achieve with traditional experimental setups. As researchers continue to develop quantum simulation techniques, they are not only expanding our understanding of quantum mechanics, but also driving innovation in technology. For instance, improved quantum simulators could lead to the design of more efficient catalysts for industrial processes, or the discovery of new materials with extraordinary properties, such as high-temperature superconductivity. In these applications, the insights gained from simulating complex quantum systems translate into tangible benefits that impact a wide range of fields, from energy production to medicine. In summary, quantum simulation is like reflecting the intricate details of a quantum system onto a digital canvas, where scientists can manipulate and study its behavior in a controlled and precise manner. By creating models of complex quantum phenomena, researchers can test theories, explore new states of matter, and bridge the gap between abstract mathematics and observable reality. This approach not only enhances our understanding of the quantum world, but also holds great promise for practical applications, potentially revolutionizing fields such as chemistry, materials science, and computing. Just as a digital artist transforms raw data into a vivid masterpiece, quantum simulators allow us to transform the abstract, often elusive principles of quantum mechanics into clear observable phenomena, opening up new horizons in both fundamental research and technological innovation. Transitioning now to our next concept. Let's explore quantum non-locality beyond entanglement, a topic that reveals how correlations between particles can extend further than traditional entanglement might suggest. In the quantum realm, it is common to hear about entangled particles, where measuring one immediately reveals information about the other, even if they are separated by vast distances. However, non-locality in quantum mechanics is a broader phenomenon that goes beyond just entangled pairs. It reflects a deeper extended connection between parts of a quantum system that defies our classical expectations of space and distance. To begin, think of two dancers performing a carefully choreographed routine. Even if they are far apart on a stage, their movements are perfectly coordinated, as if they are connected by an invisible thread. In the quantum world, particles can exhibit a similar kind of connection. When we talk about quantum non-locality, we are referring to the observation that the properties or outcomes associated with one part of a quantum system can be correlated with those of another part in a way that cannot be explained by any local interaction. It is as if the particles know about each other's states, regardless of the distance between them. Traditionally, the phenomenon of entanglement has been the most striking example of quantum non-locality. In experiments, pairs or groups of particles become entangled, meaning that the state of one particle is directly linked to the state of its partner. When one particle is measured, the other seems to instantly adjust to match, no matter how far apart they are. This remarkable observation challenges the classical notion that information or influence can only travel at a limited speed. Yet quantum non-locality is not confined to these straightforward cases of entanglement. In more complex systems, correlations can arise in extended ways that encompass multiple particles and more intricate interactions. These extended correlations are what we refer to as quantum non-locality beyond entanglement. They suggest that the quantum world is interwoven with a network of relationships that defy the idea that objects separated by space can only interact through direct local contact. One way to picture this extended non-locality is by imagining a vast interconnected web where each node influences many others simultaneously. In such a network, a change at one node can ripple out to affect distant parts of the system in a way that is not mediated by a simple direct link. In quantum systems, these types of correlations can emerge when particles interact in complex ways, leading to global patterns that are far richer than what we see in isolated pairs of entangled particles. For example, consider a large collection of particles that have interacted with one another over time. Even if individual pairs are not directly entangled, the overall system can display collective behavior where the measurement outcome of one particle correlates with those of many others. This kind of behavior is not something we would expect from classical objects, where correlations are typically limited to direct interactions. In quantum mechanics, the mathematical description of the system allows for correlations that span the entire network of particles, indicating an extended non-locality. These extended correlations have practical implications as well. In the realm of quantum computing, for instance, the power of a quantum processor depends on the intricate web of interactions among its qubits. When qubits become correlated in extended ways, they can perform computations that are exponentially more efficient than what classical computers can achieve. This ability to harness non-local correlations is one of the reasons why quantum computers have the potential to solve certain problems much faster than their classical counterparts. Another area where extended quantum non-locality plays a role is in quantum communication. Traditional communication channels rely on local sequential transmission of information. However, in quantum communication, correlations between distant particles can be used to establish secure connections. These correlations ensure that any interference or eavesdropping on the system would disrupt the delicate pattern of relationships, alerting the communicating parties to potential security breaches. In this sense, the extended reach of quantum correlations helps to safeguard the integrity of transmitted information. In experimental settings, scientists have devised clever tests to probe the extent of quantum non-locality. These experiments often involve creating complex arrangements of particles and then measuring their properties in various ways. The results consistently show correlations that cannot be explained by any local theory, that is, any theory that assumes interactions occur only within neighboring regions of space. Such results reinforce the idea that the quantum world is connected in ways that go beyond our intuitive everyday experience. One of the striking features of quantum non-locality is that it challenges our conventional understanding of causality. In classical physics, we are accustomed to the idea that an effect follows a cause in a clear sequential manner. However, in quantum systems, the presence of extended non-local correlations suggests that the traditional boundaries between cause and effect can become blurred. The outcome observed in one region of a quantum system might be influenced by events taking place elsewhere, even if there is no direct local link connecting them. This does not imply that information is traveling faster than light. Rather, it indicates that the overall state of the system is such that the parts are intrinsically linked. Moreover, quantum non-locality, beyond entanglement, opens the door to new ways of understanding and characterizing complex quantum systems. By studying these extended correlations, researchers hope to uncover deeper principles that govern the behavior of matter at its most fundamental level. This line of inquiry is part of a broader effort to unify different aspects of quantum mechanics and to bridge the gap between the microscopic and macroscopic worlds. In theoretical models, extended non-local correlations are described using advanced mathematical tools. Although the underlying math can be complex, the key takeaway is that the behavior of a quantum system cannot be fully understood by looking at its parts in isolation. Instead, the system must be viewed as an interconnected whole, where the properties of one part are inherently tied to those of the others. This holistic view is a hallmark of quantum mechanics and distinguishes it sharply from classical theories. In practical applications, understanding the extended reach of quantum non-locality is crucial for the development of next-generation quantum technologies. As researchers continue to build more sophisticated quantum devices, they are increasingly able to exploit these extended correlations to improve performance. Whether it is in the form of more robust quantum error correction, more efficient quantum algorithms, or secure communication protocols that leverage global correlations, the extended non-locality of quantum systems is a resource that scientists are learning to harness. In summary, quantum non-locality, beyond entanglement, the extended reach of correlations reveals that the quantum world is interwoven with connections that extend far beyond the simple case of entangled particle pairs. These extended correlations show that even particles that are not directly entangled can exhibit synchronized behavior, reflecting a deep underlying network of relationships. This phenomenon challenges our classical notions of locality and causality, suggesting that the quantum realm operates according to principles that defy everyday intuition. The practical implications of these extended correlations are significant, providing the basis for powerful quantum computers, secure communication channels, and new insights into the fundamental nature of matter. By exploring the extended reach of quantum non-locality, researchers are uncovering a richer and more interconnected picture of the quantum world, one that continues to inspire both theoretical investigations and technological innovations. Transitioning now to the final concept, we turn our focus to the role of the observer in quantum measurement. This idea centers on how the act of measurement affects a quantum system, a process that lies at the heart of quantum theory. In the quantum framework, a system is described by a mathematical function that encapsulates all the possibilities for how the system might behave. This description includes many potential outcomes, and until a measurement is made, the system exists in a state that reflects all these possibilities at once. When a measurement occurs, the range of possibilities is narrowed down, and a single outcome is revealed. This process is commonly referred to as the collapse of the quantum state. It is important to note that the term observer in this context does not necessarily refer to a human being or a conscious mind. Instead, it refers to any interaction or device that extracts information from the quantum system. For example, when a particle interacts with a detector or even with stray particles in its environment, this interaction qualifies as a measurement. The system and the measuring device become entangled, meaning that their properties become linked, and the outcome of the measurement is effectively recorded by the device. Consider an experiment where a single particle, such as an electron, is prepared in a state that is a combination of different possible positions. This electron is described by a wave function that includes a range of positions it might occupy. When the electron travels through an apparatus designed to detect its position, the measuring device interacts with the electron. This interaction forces the electron to choose one specific location from among all the possibilities. The original spread of possibilities is replaced by a single, definite result. In this sense, measurement is not merely a passive observation, but an active process that influences the state of the quantum system. A well-known demonstration of this effect is found in the double-slit experiment. When electrons or photons are allowed to pass through two slits without any attempt to determine their path, they form an interference pattern on a screen, a clear indication that they were in a superposition of paths. However, if detectors are placed at the slits to determine which path a particle takes, the interference pattern disappears, and the particles appear to have followed one definite path. This change is a direct consequence of the measurement process. The act of observing forces the system to settle into one outcome, eliminating the interference that arises from the coexistence of multiple possibilities. In laboratory settings, measurements are typically performed using sophisticated detectors and instruments. These devices are engineered to interact with quantum systems in precise ways, capturing information about properties such as position, momentum, or spin. When a detector interacts with a quantum system, the combined state of the system and the detector evolves in a way that records the outcome. This process is governed by the same rules that describe the evolution of the quantum system before the measurement. What changes is that the interaction effectively selects one of the possible outcomes from the superposition described by the system's wave function. The concept of measurement in quantum mechanics also involves the idea of decoherence. Decoherence is the process by which a quantum system loses its coherent superposition due to interactions with its environment. When a system interacts with external factors such as air molecules, photons, or thermal vibrations, information about its state spreads into the surrounding environment. As a result, the distinct quantum features such as interference patterns become washed out, and the system begins to behave in a way that aligns with classical expectations. In this light, the measurement process is intimately connected with decoherence. Both are responsible for the transition from a quantum state rich with possibilities to a single observed outcome. In practical terms, the impact of measurement on a quantum system has significant implications for modern technologies. In the field of quantum computing, for instance, maintaining the delicate quantum state of qubits is essential for performing complex calculations. Qubits rely on being in a superposition of states to explore multiple outcomes simultaneously. Any unintended measurement or interaction with the environment, what is known as decoherence, can force the qubits into a definite state prematurely, thereby disrupting the computation. This is why quantum computing devices must be carefully shielded from environmental interference, and why techniques for error correction and isolation are so vital. Similarly, in quantum cryptography, the security of communication protocols is based on the fact that any measurement of a quantum system disturbs its state. When information is encoded in the quantum state of particles, any attempt by an eavesdropper to measure those particles will alter their state in a detectable manner. The legitimate parties can then determine that the system has been tampered with and take appropriate steps to secure their communication channel. This reliance on the properties of measurement and decoherence makes quantum cryptography one of the most secure forms of communication available today. The measurement process also raises questions about the nature of reality at the quantum level. In classical physics, it is assumed that objects have definite properties at all times, independent of observation. In quantum mechanics, however, the very act of measurement plays a role in determining the properties that are observed. The quantum system remains in a superposition of possibilities until an interaction with a measuring device forces it to manifest a single outcome. This fundamental difference has led to extensive discussion and debate within the scientific community about the interpretation of quantum mechanics and the role that measurement plays. Experimental studies continue to probe the nature of quantum measurement. Researchers are designing experiments to better understand how the interaction between a quantum system and its environment leads to the emergence of a definite outcome. For example, experiments that involve isolated quantum systems such as ions trapped in electromagnetic fields have allowed scientists to observe the gradual transition from a coherent superposition to a state that appears classical once a measurement is made. These experiments are crucial for testing the predictions of quantum theory and for developing new methods to control and manipulate quantum systems. The insights gained from studying quantum measurement also influence the development of new theoretical models. Some models attempt to describe the measurement process as a continuous evolution rather than a sudden collapse. These models suggest that the information contained in the quantum state is gradually transferred to the measuring device and the environment over time. By understanding this process in detail, scientists hope to develop a more complete picture of how quantum systems evolve during measurement and how the classical world emerges from quantum mechanics. As researchers refine these models, they are also exploring the interplay between quantum measurement and other quantum phenomena, such as entanglement and superposition. In many quantum systems, the act of measurement is not isolated but affects multiple particles simultaneously. When particles are entangled, a measurement on one particle can have immediate consequences for its partner, even if they are separated by large distances. Understanding these correlations and the impact of measurement on them is a key area of ongoing research.